Again, it's a rich thing.
What is going on, guys? Welcome back. In today's video, you're going to see the full C++ tutorial series in one big course, in one big crash course video. And the reason I'm mentioning this here up front is because we need a general introduction here, because in the videos I'm going to say stuff like in a future episode or in a past episode we did X, Y, Z and so on. And I don't want you to be confused, because what that actually means for this particular video here is just later in the video or earlier in the video. So we're not going to actually have another episode. We're going to have this course and the individual episodes are referring to each other. But in this video, it's just later in the video or early in the video. And the reason I do this here, the reason I recycle the content and upload it in a new video is the same reason as it was for the algorithms and data structures tutorial series, that people are just more likely to watch it. Because most people, they start a tutorial series, they start to learn about it, and in the end, only a few people persist and watch the rest of the episodes. They watch episode number 1, 2, and 3, and then they drop out or something. Whereas when you publish one 4-hour video or 5-hour video course, people usually watch it till the end, or at least longer than they would watch the individual or the initial tutorial series. So this is the reason I'm repacking the content into a full course. It's good for the views for this channel, and it's also good for you because you guys learn it. So let us get right into it, into the C++ tutorial series. So let us start with the first question here, which is, who is this C++ tutorial series for? And the obvious answer is, it's for everyone who wants to learn C++ programming. But it is especially for everyone who wants to transition from a high-level programming language to C++, or who wants to learn C++ in addition to the language that he or she already knows. So let's say you already know Python, or you already know Java, or you already know C# or PHP or something. And now you want to learn C++ in addition to that. So you want to add C++ to your arsenal. Maybe you know one of those or multiple of those. And now you want to learn some lower level programming skills. If you're in that category, if you belong to those people, this tutorial series is perfect for you, because you already know basic programming. You know what loops are, you know what functions are, you know what return values are, data types, exception handling, classes, objects, and so on. And all you need to learn here is how to do those things in C++, and you need to add some concepts like pointers, templates, references, memory allocation, and so on, which is confusing in and of its own, but you already know the basics and you don't need to worry about the basics except for maybe a change in syntax, right? Whereas if you're a complete newbie, if you've never coded in your life, the question is, why are you learning C++ in the first place? So why are you learning C++ as the first language? I wouldn't say that this tutorial series is bad for you because it's bad for you. I would say that C++ is maybe not the right language for you. If you want to learn C++ for sure and you're convinced and there's no way that I can change your mind, you can watch this tutorial series. It will be fine, because I will talk about the basic concepts. I will explain variables. I will explain data types and so on. I will not say you need to already know this, but you have everything that you're going to see is probably going to confuse you. Whereas if you at least know something like Python, you know what an integer is, what a boolean is, what a for loop is, what a while loop is. And at least you're not going to be confused by that, but only by the notation or by the way it's written in C++. Whereas as a newbie, it's going to confuse you as a concept, and it's also going to confuse you the way it's written and done in C++. So if you know that you're going to learn C++ for sure, you can watch this series, but I would probably recommend learning a language like Python or Java or C# first before starting to learn C++, because C++ is very difficult and not beginner friendly at all. However, as I said, if you made up your mind already, you can watch this tutorial series as well. And then there's also another category of people who are the C programmers. There are a lot of people who already know C and they want to learn C++ as an addition to C, because C++ is object-oriented, C is procedural, and so on. And those guys also oftentimes want to learn C++. And even though you can watch this tutorial series if you're transitioning from C to C++, I think that it's going to be kind of boring to you, because you're going to encounter a lot of beginner concepts. If you're already a C programmer, you're actually operating on a lower level than C++. So you're already familiar with pointers and allocation of memory and all of those low level things. And you're also familiar with loops and data types. So you should probably watch a tutorial series that is focused on the differences between C and C++ and not a basic tutorial series like this one. Because here we're going to talk about everything. We're going to cover what a data type is, what a variable is, what a for loop is, how it's written, and so on. So if you're transitioning from C to C++, you can definitely watch this tutorial series, but expect it to be very easy for you and maybe even boring for you. This series is perfect for people who are learning Python or who are already decent at Python and now want to transition to C++. Because this channel, as you've probably noticed, has a lot to do with machine learning and Python. The focus is very hard on Python, and now we're going to add C++ to our arsenal of programming languages because there are a lot of things that cannot be done with Python, and for those things we need C++. So C++ is a great addition to Python. This combination is deadly, and this tutorial series is perfect for everyone who wants to learn both of those and already knows Python. And of course, for Java and C# it also works, but it's actually even better for Python programmers. So next, let's talk about why C++ is a good language to learn, why you should choose to learn it, and why Python or Java or C# are not enough as a language. And the number one reason that comes to mind is the performance issue. C++ is a super fast language. This does not mean that every C++ code is necessarily going to run faster than C# code, but it means that C++ has the potential, if you optimize the code, if you write good code, to be faster than C#. If you don't write good code, it's not necessarily going to be faster. But if you write good code in C++, you can have the maximum performance, or not necessarily the maximum performance, but very, very high performance. If you want to have maximum performance, you would have to go into machine code directly probably, but you can have a very high performance because you can do a lot of things manually. C++ gives you the control over your system. It's a low-level language and you can do a lot of stuff with it. One additional reason for why it's so fast is because it's compiled. And I'm not going to get too technical here, but a compiled language, what you basically have is you have source code and C++ files, header files, whatever, and you compile them into executable files. So you have executable files here, binary files, which you essentially can just run, and they have the program code in there, and they don't need any interpreter to run that code. It's compiled, you once write the code, you compile it, and then you have bytecode. Whereas in languages like Python, what you have is you have a script, and this script has some instructions, and then you have an interpreter, and this interpreter converts every single statement into bytecode on the fly during runtime. And this, of course, is bad for the performance, but even languages like Java and C#, and again, I don't want to get too technical here, but what they basically have is they have, what's happening here? Sorry. You have some source code here, some .java code, for example, and then what happens is you compile it into JVM bytecode. So you have the Java virtual machine, for example, and this then has the Java bytecode in here, but it's not actual machine code yet. So what happens then is you have an interpreter that interprets that bytecode during runtime into machine code, finally. Again, I don't want to get too technical here, but every language like C# and Java and Python is at least to some degree interpreted, where C++ is completely compiled. And this is also a reason for its performance, for its high performance. And the performance is a very, very big advantage of C++. You can max out performance if you want to. And this is also the reason why it's so highly used in AI, in hacking, in finance, especially in finance. You need to have a very, very fast execution time. The models themselves can be modeled in Python. You can use Python as an interface for design, for choosing, for structuring, but the actual code has to be written in C, C++, sometimes in assembly, because in finance, everything's about milliseconds. You can't afford to lose performance to an interpreter. You need to have it as fast as possible. Same in AI, TensorFlow and NumPy and all these Python libraries are actually written in C and C++. Python itself is written in C, C++. So Python works fine because it's the layer of structuring. You're choosing the structure in Python, but the actual code that gets run in the background is C++ or C code. Same goes for game development, Unreal Engine, C++ engine. If you write your own engine, you're going to use C++, and even Unity, which works with C#, is based on C++. It's written in C++. So whenever you're doing something like graphical computation, game development, 3D games, Java, Python are not to be taken seriously. They're Unity is a good engine. You can work with C# there, but it's also based on C++. So if you really want to get serious about game development, you probably want to learn C++. Also, whatever you want to do on a low level, like drivers, operating systems, and so on, everything's based on C, C++, assembly, whatever. And also browsers. A lot of applications are actually based on C++ because that's the C and C++ are mother and father of all programming languages nowadays, at least of the imperative programming languages. And an additional reason to learn C++, besides all these things like performance and all these application fields, is just it makes you a better programmer. It makes you a better computer scientist because you start to understand what's happening on a lower level. It's easy to just do stuff in Python. It's easy to just say, let me just run this here. But in C++, you actually understand what you're doing. You actually have to do it manually. You have to allocate memory to free memory. You have to work with pointers and templates and all that. You need to do these things manually, and you cannot just call an interface that does everything for you. And this makes you a better programmer, even if it's hard sometimes. And of course, there are many more reasons that I'm not going to all mention here. You can get super good job offers with C++. You can flex your skills in coding interviews. It's good for competitive coding. C++ is a great language to learn in general. Alright, so let's start by getting a compiler for our system, and for this tutorial series we're going to use the G++ compiler. Of course, if you have a favorite compiler that you want to use, feel free to do that. You don't have to use this one as long as you know how to get it running. It doesn't matter which compiler you use. Here we're going to install the G++ compiler, and for Windows we need additional software to do that. I think on Linux and on Mac it's either pre-installed or you can easily install it by using the default package managers. You just type sudo apt-get install G++ on Ubuntu, for example, or yum install, or I don't know how it's done on Mac, but just use the package manager. You can then install the G++ compiler, or it's even pre-installed by default. So on Windows, however, we need to get the minimalist GNU for Windows in order to run the GNU compiler. And for this, we navigate to mingw.org and click on the Downloads tab on the top right here on this page. Then we see the mingw get setup exe file. We click on download, and then it's going to be downloaded for us. I'm not going to run this here because I've already installed this mingw platform, but you can save the file, you run it, you install it. The installation process is pretty self-explanatory. And once you have that, what you do is you open up your start menu and you type mingw, then you're going to see the mingw installation manager. And here we have a bunch of packages that we can choose from, that we can install here. And the one that we're interested in is the GNU C++ compiler, the binary file. So this one, the mingw32 gcc g++ bin, the binary. You can see in the description it says GNU C++ compiler. You click on it. In my case, it's already installed, but you click on it. You mark it for installation. So I'm going to click on something else here. You just say mark for installation, but on this one here. Then you click on installation and on apply changes, and then you're going to install the compiler. Once you have done that, however, you can probably not use it directly, but you need to add it to the path variable. So you go to your start menu again and you type environment variables, or just environment. Then you get to this beautiful window here and you click on environment variables down here. And then what we care about are the system variables. And here we scroll down to the path variable here and we click on edit. So we see a bunch of entries here, and what we want to do is we want to add a new entry called mingw bin. So you want to go to new and you want to type c min gw /bin. So this is the path that you want to add. I'm not going to do this right now because I already have it, as you can see here. And once you have done that correctly, make sure that this is the actual installation path where you installed mingw, but it usually is. Once you have done that, you can go ahead and run a command line. And when you have done that, you can check if this worked by just typing G++. If it says, I don't know what that command is, for example, if I type neural 9 here, it's going to say it's not recognized as an internal or external command. If that is the case, something went wrong, but if you see something like G++ fatal error no input files, you know that the compiler is installed. So this is what you want to have. So what you're also going to need is some sort of development environment, an IDE or an editor where you can put your code into, because I would not recommend just using the basic Windows Notepad. And for this, you can go with Visual Studio Code. It's the one that I'm going to use for this tutorial series. It's well designed, well structured, it has plugins. It's open source, free, platform independent. What do you want more? It's from Microsoft, but it still runs on Windows, on Linux, and on Mac. It's the one I'm going to use. I essentially use it for everything except for Python and for Java, because there I use PyCharm and IntelliJ. So we're going to use this one for this tutorial series. I recommend it. Alternatively, you can also go with Sublime Text. However, Sublime Text costs money, but it's a very popular IDE amongst programmers. So if you want to spend some money, you can also go with Sublime Text, or you can go with Atom, which is also an open source and free editor that is hackable, customizable, if you want to look into that. If you want to have a big IDE, however, not just an editor, you can go with Visual Studio itself, with the full Visual Studio software, but then you're probably more likely to be focused on Windows, because Visual Studio only works on Windows. It's focused on Windows. I would not recommend it unless you're working on some big Windows focused projects. I'm not going to use it here. It's essentially when you're doing real desktop development with C++ for Windows. So if you're going to do that, go with Windows, Visual Studio Code, with the Visual Studio software. Alternatively, you can also have Code Blocks, which is a full-born IDE for C, C++, and Fortran. I personally am not I'm not a big fan of the design. However, if you don't mind it, you can use it on Linux and on Windows. I think it's probably also available for Mac. But that's also a good IDE that you can use. And if you want to spend some money and probably want to have the best IDE, I've never used it, but I know that JetBrains products are always awesome. So C-Line is essentially the equivalent to PyCharm and IntelliJ for C and C++. As I said, I've never used it because it costs money, and IntelliJ and PyCharm have a community edition that's free. C-Line does not. But since PyCharm and IntelliJ are great IDEs, I think that C-Line is probably also going to be a great IDE. So if you want to spend some money and you want to do C, C++ coding professionally, you can probably also look into C-Line. But as I said, we're going to use Visual Studio Code for this tutorial. All right, so the first thing we're going to do is we're going to create a new file and call it main.cpp. You can actually call it whatever you want as long as it's something.cpp. And then we're going to open it up in Visual Studio Code. And one thing that you're going to see right away is that we cannot just go ahead and start coding. You cannot just go ahead and say, okay, I want to print hello world, so let me go ahead and say print hello world. In C++, what we need is a so-called main function, an entry point for the program. Now in Python, you can just go ahead and execute simple statements because Python is interpreted, but also a scripting language. You can just write scripts and they get executed from top to bottom. Of course, you can have functions and classes and all of that, but essentially you don't need to specify this is my main function. This is the entry point of the program. You just go ahead and you start it. You can do it, but you don't need to do it. In C++, you need to do it. You need to specify a so-called main function in order to get the program running in the first place. And in order to define that main function, what you do is you type int main, then parentheses, and then curly brackets that specify the code block of that function. And since it's a function with the so-called return value int, or return data type int, which is integer, we need to add a return statement in the end here as well. We're just going to return 0. And now you might see why I meant that maybe you're going to be a little bit confused if you've never programmed before. You don't know what int is, you don't know what a function is, you don't know what a return value is, and now you have to learn all of these things. If you know Python decently, or if you're decent at Python, you know what a return value is, you know what a function is, and you know what an integer is. You maybe are confused why we write a data type before the function name, but that's all. And it might be a little bit confusing for a beginner to see all these things in the first video already, but that's what you need to do in C++. It's also, by the way, what you need to do in Java and C#. You also need a main function there. But we're going to not get too deep into the theory of what a function is and what a data type is. We're going to cover all those things in future videos. But for now, what's important is that this is the main method, main function. Sorry, it's not a method. The main function, which is essentially the entry point of the script. So everything that we want to do, we're going to put in here. By the way, this is a comment with 2 slashes. You can initialize a comment. This is not something that is taken into account by the compiler. You can write whatever you want here, whatever you want, and it's not going to have any effect on your script. It's just for taking notes, for example. Now, our goal was to write a hello world program. So we need something that allows us to print hello world onto the screen. And in Python, this was a print function. In C++, it's a cout function. The function is called cout, but we cannot just use it directly with the default stack of libraries, with the default functionality. In order to use it, what we need to do is we need to import or to include a library called iostream. And in order to include a library here, we use a hashtag symbol to initialize that we're going to include something right now, or actually to initialize it, we're using a so-called preprocessor directive, but this is a concept for a future video. And then we're going to say include iostream. This is how you include the library iostream. And this library is the input-output stream library. And we need to have an output stream in order to output something onto the screen. And in order to access the cout function, this is another concept of the C++ language, we need to access its namespace. So we have, in the iostream library, we have different namespaces, and one of those is std. And std is essentially the namespace for, or the namespace where the cout function is in. And in order to access the cout function from that namespace, we're going to use 2 colons and cout. So this is how you access the cout function of the std namespace from the iostream module. I hope that's not too complicated here. And in order to get some data into that cout function, in order to pass some data that we want to print onto the screen to that cout function, we do not call it, but we send the data to it using angle brackets or using arrows. So what we do is we do this here, 2 angle brackets, 2 opening tags that point towards the cout function, and then we feed the text into that function. So we say hello world, like that. So this here is a string, this here is a text, and we feed this text here using those 2 tags here into the cout function. And we can now go ahead and also add an end line tag, which is essentially just a line break. So if you want to start a new line, you do that. And we add another or 2 more of those arrows, and then we say std end line or endl, which is the end line tag here. So this is actually what we need to do. And as you can see, we end every line, every instruction with a so-called semicolon. This is also new if you're used to Python only. You don't have semicolons there. This is what you do in order to signal that this line is now over. You don't need to, or actually the compiler doesn't need to worry about more code coming. This statement is done, and we're done with this line of code. So this is actually the script that is producing a hello world program, and we're now going to compile it using G++. So in order to compile the script, what we do is we run a terminal here by clicking on new terminal, and then we navigate to the desktop where we have written our script. Then we can use the G++ compiler that we installed in the last video and say G++ main.cpp. By specifying the -o tag here, we can also specify what we want the file name to be of the executable file. In this case, just main.exe. And by clicking enter, we can see that we have an executable file on our desktop. When we run it, we're not going to see anything, of course, because the output happens and then it's gone. But if we go ahead and run it in the terminal, we can just say main.exe. You can see it says hello world. All right, so as always, let's start with the code structure first. We're going to say include iostream, and then we're going to define our main function here, return 0. And before we get into variables and data types, one thing that I wanted to show you is that you can also use the whole std namespace that we used in the last video. So what we did is we said std cout and then hello world and std endline. This is what we did. What we can also do, if you don't want to always specify that std namespace in front of every function or tag or whatever you're using out of it, you can go ahead and say using namespace std. And then you can just get rid of those std prefixes here. However, why didn't I show it to you in the first video is because I don't think that you should get used to that way of programming, because using namespace std and then just writing cout and endline and so on is not considered to be best practice. I mean, of course, you don't always have to code in best practice, and it works. You can definitely go ahead and write code like that. But if you're going to write clean C++ code, you're not going to do it like that. Because first of all, you're just using cout and endline from std right now, and it doesn't make sense to use the whole namespace because of that. If you're only using cout, endline, maybe 1 or 2 other things, it doesn't make a lot of sense to use the whole namespace, to just include or import or whatever, to just specify that you're using the whole namespace, because it's just too much, so to say. It's not clean. It works, it doesn't have any problems, it doesn't bring any problems into your program yet, unless you have a second namespace that also has something like cout or endline, because then you run into some problems. But it's just not the general accepted best practice way to say using namespace std and then cout and endline. You're always going to see this in code examples because it's just more convenient. And if you're doing some videos, if you're writing a blog post, if you're just practicing, if you're just writing some sample code, you can definitely do it like that. And we can also definitely do it like that in the tutorial series here. I'm not going to do it like that, but we can do it because it's not wrong. But I don't want you to get used to that way of programming, so we're not going to do it like that. I want to show it to you that it's possible, but we're going to write the best practice type of code here. We're going to always specify std before we use something from that namespace. So that's just something that I want to show you before we get into variables. All right, so let's talk about variables now. Variables are essentially just placeholders for values in programs. So maybe variables from mathematics already. They're just stuff like x equals 10, or y is a function, or y is some list or some set or anything in mathematics. And it's the same way in programming, just that we have a lot more data types. We have integers, so whole numbers. We have floating point numbers. We have Boolean values. You have text values. You have lists and collections and structures. And later on, even objects, whole objects that represent stuff like a person, for example, can be stored in a variable. And in contrast to languages like Python, for example, C++ is statically typed, which means that we have to specify the data type of a variable before we can actually assign a value to it. In Python, for example, for those of you who know Python, you know that you just go ahead and say a equals 10, and then the interpreter already knows that a is going to be an integer for now. And later on, you can also say a equals something else, like hello. So hello is a text, so a is no longer an integer, a is a so-called string. And in Python this works. In C++ we don't do things like that. In C++ what we do is we specify the data type first. And if you want to have an integer, you specify the keyword for the integer, which is int, and then you specify the variable name. So you say int x, for example, int x equals, and then you can say int x equals 10. And if you want to change the value of x, what you do is you just say x equals 90. Again, don't forget the semicolon for those who are used to Python. And you can change the value as many times as you want, of course. You can say x equals 20, x equals 90, but you cannot change the data type. You cannot just go ahead and say x equals hello, because then the compiler will tell you that this type is not compatible. You have an integer and you want to assign something else to it. This is not an integer here. You want to assign a string or something else, but it's not an integer. It's not compatible. So this is statically typed. You have to specify the data type first, and then you can assign a value to it. So that's not too complicated, but let us now go ahead and talk about the different data types. And we're going to talk only about the primitive data types now. This means just basic stuff like numbers and texts and Boolean values, and not stuff like lists or structures or classes and objects. So just the primitive data types here. And we're going to subdivide them into three categories. First of all, the numerical data types. Second of all, the textual data types. By the way, these are just my terms, so maybe they're not 100% scientifically accurate. And then we have the Boolean. Okay, so the numerical data types are essentially you have either whole numbers or floating point numbers. But there you also have different types of floating point and different types of whole numbers. So you have the integer. This is the basic one that we saw already. Int I equals 10, for example. But then you also have the short and the long. And the short and the long are actually just integers. In fact, you don't even have to say just short. You can say short s equals something. But you can also say short int s equals something. And that's actually the same thing, because short is just another type of integer. And the only difference is the memory value or the memory amount that they occupy. Now, this is something that you never worried about in Python, because in Python you just, you define stuff and it happens. In C++, we're operating on a lower level, and this means that we need to care about stuff like memory management. We need to know, do I really need an integer, or is a short enough maybe? The difference, of course, is that they occupy a different amount of bytes. So we can actually look at how many bytes they occupy by using the sizeof function. So we're going to say std cout, and then we're going to say integer int. So this is just some text. You can write whatever you want in here. And then you say size of int, and then maybe an end line in the end. So what this function is going to give you here is it's going to give you how many bytes an integer occupies in the RAM, in the memory. And we can go ahead and open up a new terminal and compile this main.cpp main.exe, and then we can go ahead and run main.exe, and you can see that we get 4. This is 4 bytes, and a byte is 8-bit. I'm not going to explain the binary system to you, but if you know the binary system, you have essentially 1 byte being 8-bit, which means that 4 bytes are 4 times 8 bits, which is 32 bits. It's quite a large number, and we can go ahead and do the same thing here for the short, and you're going to see that a short occupies less amount of memory. So we can say short size of short. You can also say short int, it doesn't matter. And then we compile it again and run it again. And you can see a short only occupies 8 bytes. We can do the same thing for long as well. And there you will notice something that's quite interesting. And it is that in C and C++, oftentimes things are just not defined. Now in this case, in my computer, it's going to say that a long also has 4 bytes. It doesn't have to be that way on your system. The definition for a long is only that it has at least as many bytes as an integer. It doesn't mean that it has to have more. It can have more, but it has to have at least as many. So maybe in your computer it's going to have 8. Maybe it's just going to have 4. It doesn't matter. It's not defined, and we'll encounter many things in C and C++ that are not defined, that are undefined. We don't know what's going to happen when we do them. They're not forbidden, we just don't know what's going to happen. And this is also one of those, we don't know what size of long will return on every system. So what does that even mean? What does it mean that a short has 2 bytes and an integer has 4 bytes? For this, we're going to open up the Windows calculator. So just open up your calculator and set it to programmer mode, and then we can talk a little bit about the binary system. We're not going to explain the whole binary system, so if you're not familiar with it, you can just ignore this part or just watch it and accept it as the truth. But essentially, if you have 2 times 8 bits, or 2 bytes, 2 times 8 bits, you have 16 bits. And 16 bits means that you have 16 zeros and ones that you can set, which means that you have a certain range of values that you can use for this short. So for example, if I set all the values, so all the individual bits, all the 16 bits to true, I would have 1, 1, 1, 1, this is 4, then we have 8, then we have 12, and then we have 16. So this would be 16 bits set to 1. And if you convert this number to decimal, you can see that that is the number. That is the maximum number that we can represent using 16 bits, using 2 bytes. Now we can go ahead and copy that number, and we can say short as equals that number without that here, and we can go ahead and print it. But you're going to notice an odd thing here. So I'm going to say actually just s itself, end line. You're going to notice something that's a little bit odd here. It's going to not work the way we want it to work, because it's going to give us -1. And even if we decrease it or increase it, it's not going to give us what we want. And this is because we're not using a so-called unsigned short. The difference between a signed and an unsigned short is that if you have a signed number, like that, this is the default, we don't need to specify it, but if it's signed, this means that we start at 0 and we go into the positive direction and into the negative direction half as many bits as we can, so to say. So instead of using the numbers 0 to that maximum number here, what we do is we go from 0 to half that number, and from 0 to negative half that number. I hope this is not too confusing. If we want to use all the 16 bits only for positive numbers in C++, what we do is we say unsigned short. Because by doing that, we can use the full range from 0 to 65,535. So we can go ahead and compile this, and you can see that we get that value. Now, what happens if I add one more to it? What happens if I go beyond that number and try to add one additional bit? Because in order to represent that number, 16 bits are not enough. We need to add one more bit. What happens if I try this with a short that only has 2 bytes? You can see what happens. actually it stops. Actually, this is not what I expected, because usually it gives you an overflow. Oh, it didn't compile, that was the problem. Yeah, as you can see, we get a warning, a compiler warning that says overflow, something with overflow. This means that we're going beyond the limits. This means that we're going beyond the capacity that we have, and instead of saying, no, you cannot do this, it's going to just overflow. So it's going to start counting from the beginning again. So if I run this, where is it? There you go, you can see I get 1, because I surpassed the maximum by 2. If I surpass it by 1, we will get 0. And if I surpass it by 3, so if I say 8 here, we're going to get 2. So it just begins, it just starts all over again, because it doesn't have any capacities. It just has 2 bytes, and if you try to store a number that's too high into it, it's going to overflow. And of course, this can be done for integers as well. We can go ahead and say unsigned int, and we can think about what this means. We have 4 bytes, which is 4 times 8 bits, and instead of doing this in binary, we can just say f. F, as you can see, is 4 ones, so f is 1, or f is half a byte when you're using it in hexadecimal. So we can say f, 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 f. So we have 2 bytes now, then we have 3 bytes and 4 bytes. So this is the maximum number that can be represented with an unsigned integer. Let's see if that's true. We can say unsigned int equals that number, and we can run the script, not the script, the program. Always making that mistake. And you can see that this number is represented correctly. And if I go ahead and say 6 here, so 1 more than is allowed, you can see I get a warning here, and we start at 0 all over again. For the long, it's going to be the same on my computer, since it's also 4 byte. But what we can do if we really need more, we can go ahead and say long. I'm not going to change the string left here, so just ignore it. But we can go ahead and try a long. This is something that is going to have a little bit more space. As you can see, it has 8 bytes. And we can go ahead and see what 8 bytes are. 8 bytes are essentially 1, 2, 3, 4, 5, 6, 7, 8. And as you can see, the Windows calculator itself gets an overflow, because that's too much. It doesn't store anything that's more than just a long. So we're not going to do the same value thing here, but essentially if you really need a lot, you just say long. Otherwise, integer should be enough for most calculations. But you can see that in C++, we need to worry about that. In Python, you can just define any number, and it's going to adjust, and it's going to allow you to have that number no matter how high it is, how large it is, as long as you have enough memory left in your RAM, of course. But this is something we actually need to take care of in C++. Alright, so besides those whole numbers here, we also have floating point numbers, and for those we have the 2 data types, float and double, whereas the float is less accurate and the double is more accurate. So the double has, I think, 8 bytes, double, and the float has, I think, 4 bytes. And we can see if that's true by just compiling and running. Yeah, as you can see, 4 and 8. And this means that the float stores up to 7 digits of accuracy, and the double, I think, was 15 digits of accuracy. And of course, if you need even more accuracy, what you do is you say long double, and then you have more accuracy. But yeah, this essentially means if you have a number like 16.7 or 16.75, you better store it in a float, because it needs less memory. So we can say float f equals 60.78, for example. And if you have a larger number, you say double d equals 90.8765, 12. And if you need even more than that, you just say long double ld equals, I don't know, 9.18675488976, and so on. So depending on the accuracy you need, you choose the floating point value that you want to use. Now, before we get to the next data type category, I would like to show you something. If you want to know the limits, the boundaries of a data type, what you do is you go ahead and include the library limits. So you say include limits.h. And when we have done that, we can use, or we can access the maximum and the minimum values for each data type. So we can go ahead and say std cout, and then we can say int underline max. This is the maximum value for an integer. at least for a signed integer, I think, if I'm not mistaken. Let's see if that's true. And we can go ahead and say std endline. Actually, let's get rid of all of that here. We don't need this anymore. And if we run this here, yeah, it's a signed one. As you can see, it's half the actual maximum. And we can do the same thing for the minimum here. Int min. And it works as well. Now I think we should also have something for the unsigned integer. So uint max std endline, which stands for unsigned integer. And yeah, there you can see the maximum. So if you want to access it real quick, you can do it like that. And I think this should be available for all numerical data types. So short, actually short is not available. Oh, actually shrt max is short. There you go. And it's probably also available for a long. So long max. And as you saw, you also have long max. So we can see what that is. And line. And let's see what we get as an output here. As you can see, this is the maximum value for long int. Great, so let's get into the textual data types. And the first one is the character, the char C or character C. What we do here is we define a character by using a single quotation mark. And this is just one character. It's one character. I think character uses the UTF-8 encoding, which means that 1 byte is enough to represent all the UTF-8 characters. So a character we're going to see has 1 byte. You can go ahead and print that std cout size of character. And when we run this, you will see it has 1 byte, which means 8-bit. Did I say 4-bit? Sorry if I said 4-bit. I mean 8-bit, of course. So this is sufficient to represent all the different UTF-8 characters. And we can go ahead and do it like that. And you can see A, but I think we should also be able to assign a number like 19, for example, and it would typecast it into a character. As you can see, yes, 19 is this character. Something like 80 should probably be a letter. Let's see if that's true. Yeah, as you can see, uppercase P is the UTF-8 code 80, or maybe the ASCII code, but I think character is using UTF-8 encoding here. So a character is just a number that represents a character, okay? That represents a character, and this character has a certain identification number. In this case, 80 is uppercase P, for example. So that's a very simple data type, just has 1 byte, and it represents characters. And now we have another textual data type, which is the string. And the string is actually just a collection of characters. Now, this is a little bit more advanced. You need to know about lists and arrays and so on. But a string is essentially just an array of characters. It's just a C array, a char array, so to say. But we're going to talk about that in a future video. For now, just use the std string. And the string is just a text. The string is a text. It has 24 bytes, I think. So hello world would be a string. And we can go ahead and print this string here. And we can also print its size. I think it should be 24 bytes if I'm not mistaken. So size of string should be 24. Oh, I got an error here. Oh, of course, std string. Yeah, as you see, 24 bytes, and hello world is a text. So whenever you work with text, you're using strings. Individual characters, you use chars. Okay, so last but not least, for the primitive data types, we have the Boolean. The Boolean is also a very simple data type. It also has only 1 byte, and that's actually even too much for it, because the only 2 values that a Boolean can have are either true or false. That's all it has. It's just a truth value, so it's either 1 or 0, true or false. And we can go ahead and define a Boolean with the bool keyword, so bool b equals true, for example. And then we can go ahead and see out that value and line. And you'll see that we get 1. This is important because even though we have the keyword true, a Boolean is just 1 or 0. So we can treat it as a number. Like not necessarily a number that you can do calculations with, but you can check for 0 or 1. You can also define it By saying bool b equals 0, this would be false. And it will also print 0, of course, but it's not all of a sudden an integer, right? It's not just an integer or a short that you can do calculations with. It's 0 or 1. It's a Boolean value. It's true or false. It's also represented as 0 and 1, but it's still true or false. And this is something that we're going to need when we get to conditions, when we get to comparisons, when we want to know if something is true. You know, in programming, you have certain conditions where you can say if something is true, do that, otherwise do that. And the value that this comparison, if something is true, or this statement gets you, is a Boolean value. So when you try to say if the input of the user is valid, this is a Boolean value. The input is valid, true, the input is invalid, false. Or if this number is less than this. And this is also a comparison that gives you a Boolean, which is either true or false. So this is a very important data type. We can also look at the size of it. As I said, it's 1 byte. Not a clear screen. Come on, compile. Main axis, as you can see, 1 byte. By the way, one thing that I didn't mention here is that you can not only get the size of the data type itself, you can also say get the size of b, which will be the same in this case, but sometimes it differs. So you can also get the size of a particular variable. All right, so we're going to start out with the first category of operators here, which are the so-called arithmetic operators. And operators, generally speaking, are just tools, simple tools that allow us to perform operations onto values, onto objects, onto variables, and do something with them. For example, we have arithmetic operators that are mainly used for calculations, arithmetic calculations. Then you have stuff like comparison operators and stuff like assignment operators and so on. We're going to start out with the arithmetic operators first because they are very simple. They are just the basic mathematical operations. So I have arithmetic operators, and these are just essentially addition, subtraction, multiplication, division, and the modulus operator that we're going to talk about in a second. So let's say we have two variables here, int a equals 10 and b equals 20. What we want to do is we want to go ahead and print the sum of those. So what we do is we say std cout a plus b, and then std end line. So this is a basic addition. This is just a plus b, 10 plus 20. Of course, we can also go ahead and do one more. So we can say a plus b plus 70, for example. So in this case, we would get 100 because we have 10 plus 20, which is 30, and then plus 70 is 100. And now we can go ahead and compile and run this here. And you can see that 100 is the result here. Very simple. We also can do the same thing with subtraction. And if we do that, in this case, we would get 10 minus 20, which is negative 10, plus 70 would be 60 in the end. And we can do the same thing, of course, with multiplication and division and so on. So in this case, we would say 10 times 20, which is 200, and then we would divide by 70. Maybe let's divide by 40 and get 5 as a result here. So as you can see, we can just combine these arithmetic operators here. So I think division, multiplication, subtraction, and addition are pretty self-explanatory. What's maybe not that self-explanatory is the modulus operator. It basically just gives you the remainder of a division. So let's say we have a number like, I don't know, 7, or let's say 10. If we divide 10 by 2, what we get is 5 and a 0 as a remainder, if we're focusing on integers, of course. So because we're not going to, we're not calculating the decimal places, we're just calculating the integer result and then the remainder of the division. So in this case, it would be 0, so we can go ahead and say a modulo 2, or actually a modulo b, which is 2. And if we run that, you can see that the result will be 0 because 10 divided by 2, or 10 is divisible by 2, and therefore we don't get a remainder. If we go ahead and say b equals 3, we would get 10 divided by 3, and this would be 9, and 1 is a remainder. So in this case, if we go ahead and compile and run, you will see that we get 1. And of course, if I go ahead and do something else like 4, we would get 8 and 2 as a remainder. So actually, let's just delete that here and say F6. And you can see we get 2 as a remainder. So this is how the modulo operation or the modulus operator works, just calculating the remainder of a division here. All right, so next let's talk about the assignment operators, and you already know the basic assignment operator. It's used to assign the value on the right to the object or variable on the left. So whenever we say int a equals 20, this equals here is the assignment operator. It's the most basic assignment operator just takes the value on the right and assigns it to the placeholder on the left. Very simple, but this is not the only assignment operator that there is. And we can go ahead and combine the arithmetic operators that we already know with the assignment operator. So let's say we have this variable here and it has the value 20, and now we want to increase this value by 20 or by 10. Let's say we want to increase it by 10. Now, one way to do this is to just go ahead and say a equals a plus 10, because then what we do is we say, okay, get the value of a, the current value of a, add 10 to it, and then store this into this left variable here. And of course, it's going to be increased by 10, so the result is 30. And we can go ahead and print that by just saying cout a, std end line. And if we do that, we're going to see that we have 30 as a result here, but this is not the only way to do it. We can also go ahead and use a specific operator for that, and this is the plus equal operator. So we have this operator right here, and this does the exact same thing. So it's just another way, a more compact way of writing the same thing. It's essentially just increasing the value of a by 10 and storing it into it. So we're not just calculating a plus 10, we're also saving the result into a as a result. So if we run this, we're going to get 30 as well. And this does not only work with addition, you can also do that with subtraction, you can do that with multiplication. So in this case, you would get a times 10 and save the result into a. So in this case, it would be 200. Oh, I clicked the wrong thing. There you go, 200 here. And you can do the same thing with division and even with the modulus operator. So in this case, if you go with the modulus operator, you would get 0 because 20 is divisible by 10, and therefore we have a 0 as a remainder. Also, this is not just limited to arithmetic operators. There are also other operators that can be used for this. There is a category called the bitwise operators that we're going to mention at the end of this video or later on in this video. But we're not going to learn about them in detail because they're not so important. We're going to talk about that. But you can also combine those bitwise operators with the assignment operator. So instead of using, let's say, one bitwise operator is this one here, this symbol here, what you can do is you can also use it like that to store the result of the bitwise operation into a. That we're going to talk about later, so don't be confused about that symbol here, that operator that you don't know yet. But essentially, you can use the assignment operator in combination with other operators to save the result of the operation into the variable. Now, we also have two other operators that I would consider to be assignment operators because they're very similar to the combination of the basic assignment operator and the arithmetic operators. And those are increment and decrement. And these two operators are something that you will not find in Python. So if you're only used to Python, you probably don't know about them. And they're written like this. Let's say we have an integer a and a equals 10. Increment would be something like a plus plus. And this means essentially this is the same thing as saying a plus equals 1, which is the same thing as saying a equals a plus 1. So all these three commands here are doing the same thing. The difference here is, though, that we use a++, first of all, because it's a more simple way to just increase the variable by 1 or the value by 1, but it's also used whenever you want to return the value. So a++ is one way to do an increment, but you also have plus plus a. And the difference between that is that if you say a++ and you feed this into a cout, for example, or actually before I explain it, let's just do it. Let's say we have std cout a++, and then we say std end line. What you will get here is you will print a++, or you will print the value of a first because a is fed into C++, and then it's going to be increased. Whereas if you say plus plus a, you're going to first increase the value and then return it to the function or feed it into the function. So let's just go ahead and run this, and you're going to see that we have 10 here because first we print or we output a and then we increase it by 1. And if you go ahead and do the same thing here afterwards without the plus plus here, you're going to see that a is in fact or was in fact increased by 1. We can go ahead and do that. But it's not printed the first time because the increment happens after the printing. Whereas if I say plus plus a, it's going to first increment the value and then print it. So we can go ahead and actually let's go ahead and press F6 again. There you go. You can see it's immediately printed as 11 because we first increase it and then output a. And this also goes for the decrement operators, so we can do the same thing with minus minus. If we do it before the a, so if we say minus minus a, we're going to get 9 as the first print because it's first decreased. It's first we subtract 1 and then we print a, or the result of that variable, the content of that variable. And if we say a minus minus, it's going to first print a as it is and then decrease it by 1, as you can see in the console results here. Alright, so another category that we have are the so-called comparison operators or relational operators. And as the name already says, they're used for comparisons, but they're especially important when we come to decision making, when we get to conditions, if statements, but also when we get to loops. So those operators are going to be very important when we make the code a little bit more conditional. So not just do this, do this, do this, but do this if something is true. We're going to use a lot of those comparison operators in if statements, in for loops, and while loops, and so when we get to them. But for now, they're essentially, I don't know how many there are, I think 6 comparison operators. The most basic one is the equal operator, so it's not one equal sign because that is associated with assignment. We use 2 equal signs to ask is something equal to something else. We use an exclamation mark and an equal sign to say is something not equal to something. And then we have the basic stuff like less than, greater than, less than or equal to, or greater than or equal to. So those are the comparison operators here, and all of those return a Boolean result. So when we have one value here on the left, a for example, and another value here on the right, the result of this operation here is not another number, it's not a string or something, it's a Boolean. So it's either 0 or 1, false or true, no or yes. So when we say a equals b, this is a statement, and the compiler or the computer is going to tell us that this is the case or this is not the case. So 0 would mean no, this is not a true statement, and 1 would mean yes, this is a true statement. So let's say we have int a equals 10 and b equals 20, and then we're going to stdc out the result of a less than b. This is a comparison, and the result of this comparison is obviously 1, as you can see, because 1 means true, and this is obviously a true statement. 10 is less than 20. We can do the same thing with greater than, and you're going to see that we're going to get a 0 here. So if we run this here, we're going to get 0 as a result. And if I go ahead and say a equals 20 and b equals 20, I'm also going to get 0 for the less than operator. But if I go ahead and ask, is a equal to b, I'm going to get 1 because they have the same value. And of course, I can also go ahead and do the not equal thing. So let's say I'm saying b is 30 and a is 20. I can say, okay, a is not equal to b. Is this true or not? Yes, it's true. As you can see here, we have a 1. It's true. And of course, we can say is a less than or equal to b. So in this case, it's less than b. So less or equal to is true because it's not equal to b, but it's still less than b, so it's true. But we can also set a to 30, for example, and it would still be true because the comparison is of course true. So this is how comparison operators basically work. They tell us if something is true or not, and this not only works for integers or numbers in general. This also works for objects and strings and so on. If you implement the right response to the operator, of course, but that is something for another video, so it's a little bit more advanced. But essentially, you can just use these operators to compare certain values, certain variables, certain objects, and then based on that comparison, based on that Boolean result, you can do certain things with if statements and loops that we're going to learn about later on. Now, one more thing that we can do with comparison operators is we can combine them into more complex, more sophisticated comparisons. And in order to combine comparisons, we need to use logical operators. So let's say, for example, we have a number a again equals 10 and b equals 20 as always. And then we want to say, okay, is a less than 20 but still greater than 5? In this case, it's true. So what we want to know is we want to know if this value here is less than this value, but still this value has to be greater than 5. So what we can do is we can say stdc out, and we would say, okay, a is less than b, but we also want a to be larger than 5, greater than 5. So in order to combine both of those statements here into one big comparison, to one statement, we're going to use logical operators. And here we can either use the and, we can use the or, and we can use the not, whereas the not is not applied to two sides, so we cannot say left, not right, but we essentially use the not on one statement. So if this one statement is true, it's going to be false, and if it's false, it's going to be true. But in this case, we need the and logical operator, so we use two and symbols here. We're not using one because one and symbol means something else in C++. First of all, it's used for pointers, but if you're not using it on variables, it's also used for the bitwise AND operation that we're going to talk about in a second. But this is essentially how you combine two Boolean values. So you say this here needs to be true and this here needs to be true. If one of them is false, the whole thing is false. So in this case, we can go ahead and say std end line and print this. We have a problem here. Oh, of course, this whole thing needs to be put into parentheses because otherwise we get an error, a compiling error. And as you can see, we get a wonderful result because A is less than B, 10 is less than 20, and 10 is also larger than 5, so greater than 5. In this case, both sub comparisons are true, and therefore, since we combine them with the and, both are true, so the whole thing is true. Now, if I say, okay, A needs to be less than B, but A also needs to be larger than 15, we have the left side being true because A, 10, is less than 20, but A, 10, is not greater than 15. So one part of the whole thing is wrong or false, and therefore the whole thing is going to be false. As you can see, when we run this, you can see that we get 0 as a result because the right thing, the right sub-statement, the right sub-comparison is not returning true. And this operator here, this and operator here, demands that everything, both sides, have to be true. And of course, we can go ahead and substitute it now with a or. This is, I don't know what this operator here is called, to be honest. But two of those operators here are considered the or statement, the or logical operation, which means that one of them has to be true, both can be true, but at least one of them has to be true. Okay, so if both are wrong, the whole thing is going to be wrong or false. But if one of them is true, that's enough. So even if that's not true, but that is true, or the other way around, it's totally fine and the whole thing returns true. So this is the or operator. It's not exclusively or, so it's not XOR, it's not either one or the other, it's at least one of them. Both of them is also fine. So this is the difference between an XOR operation. And here you can see we get 1 as the result. This is the basic or operator. Of course, if I say, okay, it has to be larger than B and also larger than 25, for example, it's going to give us 0 because neither one of those sides is true. And then finally, we also have a not operator. Essentially, if we have something like A is less than B, we can add an exclamation mark before that whole statement here. And this means that whatever we get here as a result, negate it. If it's true, make it false. If it's false, make it true. And then we get the result. So in this case, A is less than B. This would return true, which is 1. But by applying this not operator here, we would get 0, so false. And you can see that we get 0. And of course, if I swap this here, we're going to get 1. Because it's false, and then it's true. And we can, of course, combine all these queries here. We can say not this and something else. And then we can use the whole statement here and make it or something else and so on. We can combine all these comparisons with logical operators to make a big whole statement about what has to be true in order for this whole thing to be true. So we can combine them using logical operators and build all kinds of different logical statements and structures here. All right, so last but not least, we're going to mention bitwise operators, but we're only going to mention them here for the sake of completeness. If you want to learn about bitwise operators, I recommend you to use Google to just type in bitwise operators C++. I'm not going to teach them here in this tutorial series because I think that it would not give you a lot of value. I've never used bitwise operators in my life, in my programming life, unless I was doing some coding challenges. So whenever I did something in HackerRank or Code Wars, maybe I needed bitwise operators 1 or 2 times there for some creative solution to solve some problem because there were artificial constraints on what I'm allowed to do. But I've never used bitwise operators in a project, and I don't think that you're going to need them anytime soon, unless you know you're programming in assembly or something. And if you need them, if you really think that you need bitwise operators, just go ahead and Google them. It's not too hard to learn them, but I don't think that I want to make this video even longer just to teach you bitwise operators. However, I'm going to tell you what they basically do, and they are just performing binary operations, bitwise operations. So let's say we have a number here like 15. 15 is a decimal number, and we can represent it in binary digits based on powers of 2. I'm not going to go into too much detail here, but essentially the number 15 looks something like that. Whereas the number, I don't know, 12 looks something like, let me think about it. We have 8, then 4, and then 0, 0. Yes. So those are the two numbers, 15 and 12 in binary representation. And what bitwise operators do is they apply certain logical operations onto the individual bits. So the AND operator, the AND bitwise operator, would be something like that. And what it does is it goes through all the positions and combines them. So it says 0 and 1. Okay, that's 0. 0 and 1. Okay, that's 0. 1 and 1. That's 1. 1 and 1. That's 1. So the result would be 1, 1, 0, 0. Actually, it would just be 12 again. But this doesn't have to be the case. So let's say, for example, we have something like that. Or actually, in this case, it would be the same. But let's say we have something like that. This would result in 1, 0, 0, 0. So another number. So again, I'm not going to talk about the individual bitwise operators, but that's what they essentially do. They perform different logical bitwise operations here onto the individual bits. And this can be useful in some scenarios, but for our purposes, it's not something that we need. All right, so up until now, our programs were pretty static. We didn't have any user interaction. We didn't have any information from outside of the program code. Everything we did was hard-coded. Every value that we chose was hard-coded, and when we wanted to change something, we had to change the code and recompile it. And we're going to change this in today's video by introducing user input, by learning how to process user input. And you already know about the function stdcout, which takes some text and puts it out onto the screen. But there's also the function called cin, so stdcin, and it's the opposite thing. It gets something from the console and gets it into the program code, so to say. And let's say we just put out something like, please enter your name. And we're not going to do an end line here because we want the user to continue to put the text into the same line. Now what we can do is we can call the cin function, but since this function is getting something from the console window, from the user, and putting it into the program, this function is called cin, and also we need to use the arrows in the opposite direction. So in this case, we don't say cout and then we feed something into it. We say cin and extract something out of it. So in this case, we can put this into a variable, and let's create this variable by saying std string name, and then we say stdcin, the result shall be saved in name. And after that, we can go ahead and say your name is name, like that. So when we have this, we can go ahead, press F6, enter the name, let's say neural 9, and you can see your name is neural 9 in this case. So this is how you process user input. You just say cin, and whatever you get out of cin by pressing enter in the end, you save into the variable that you define. Now you can also do this with other data types. So if you now pass 10, it's going to be saved in a string. So it's going to be not 10 as a numerical value, but 10 like this as a string, just a text 10. But if I change this, for example, to let's say int h, and we say please enter your age, and we want to see in the age, and then you say your age is age. This is now an integer. So whatever we put into this program is going to be considered an integer. We don't need to typecast it. It's going to be typecasted automatically. The cin function returns, or whatever we extract out of the cin function will be the data type that we need, in this case integer, of course. I'm not sure if this is going to work with all classes and objects and data types, but it works for int, it works for float, it works for strings and so on. So for the primitive data types, it seems to work, and we can look at it. Enter your age, 10, your age is 10, and to see that this is actually an integer and not just a string, you can go ahead and add 20 here to it, just to see what happens. And when we now enter 10, we get 30. And since we can calculate 10 plus 20, we know that age is in fact an integer, as we already stated. So this is how you process user input in C++. By the way, for those of you who are wondering what I'm using to compile the program code all the time, I'm using an extension here in Visual Studio Code called C++ compile run. It is by Daniel Pinto 8ZZ6. A very basic extension. You just install it and then you can press F6 to compile the code and run it. And you can press F7 to run it with some additional parameters. For those of you who are wondering what I'm using to compile all the program code here by just clicking F6. All right, so with the knowledge we now have, we should be able to easily implement a basic addition calculator with the numbers put in by the user. So let's say we have something like int and 1 and 2. Then we say cout. Actually, by the way, for those of you who are wondering, you can also go ahead and say using std cout if you just want to use std cout and not import the whole namespace std. So if you want to do that, you can do that with cout, we can do that with cin, and we can do that with endline. I'm not claiming that this is in any way best practice or something, but since we're just learning, we can use it like that. Usually I think it's best practice to just say std all the time, so to specify it separately or individually every time. But since we're just learning here, it doesn't matter too much if we're using best practices. However, we can now go ahead and just say cout, and we can say, please enter the first number, like that. And we're not going to use an end line here. And we're going to do the same thing for the second number. And in between, we're going to say cin and 1 and cin and 2. And in the end, what we're going to do is we're going to say cout sum is, or let's use an English sentence here. The sum is n1 plus n2 end line. And if we compile and run this, you can see we can enter a number here. Let's say 8 and 19, and we get 27 as a sum. So that's how you can build a basic addition, dynamic addition calculator in C++ by using user input and then a basic arithmetic operation. Now, one more little thing that we can do with the cin function here, especially when we're learning C++, is we can just wait for user input before we terminate the program. So let's say we have something like hello world, like in the first video where we did some actual code, hello world. The problem is when we go ahead and compile this here and run it, of course. Oh yeah, we need to use std again. When we just go ahead and compile this and run this, it's going to work. But as you can see, the script, the program terminated immediately. And if we go ahead and go to the desktop here where this is compiled and we run it, you can see that it opens up down in the taskbar. You can see it opens up for a second and then it's gone again because it's already terminated. You just print hello world and that's it, and you're gone. If you want to wait before you terminate for a user input, what you can do is you can say std cin.get. This essentially just waits for some user input before it proceeds with the code. And since it's not proceeding, since it's not done with everything yet that is coded inside of this program, it's going to wait and the window is not going to disappear before you click enter. So we're going to compile this here. And when we do this, of course we need a semicolon here. When we do this, you can see that it says hello world, but it's not terminating, it's still running. When I press enter, it's done. And we can see that when we go ahead and run this executable file here, we can see hello world actually waiting for us for more input. And I can put in some stuff here and it's still not terminating, but when I click enter, it's going to terminate. And this is something that we can use in order to pause and to wait for the user to click enter before we actually terminate the script. All right, so for this video, we're going to make some using statements here. We're going to say using std cout. We're going to say using std endline, and we're going to say using std string. Now, again, not best practice, or actually, I don't know if that is best practice, but usually you don't just say using namespace std, which we didn't do here, but I'm also not sure if that's the best practice way to do it. However, we're going to do it for the sake of simplicity here. And typecasting or type conversion, what you basically do is you take one data type and convert it into another data type. And there are many reasons for that. So let's say, for example, we have some string and this string contains a number and we want to have this number in order to be able to do some calculations with it. So let's say we have something like string s and this string is 10 or 1023, for example. And what we want to do with that string is we want to do some calculations. We don't want to just take this as a text. We want to take this as a number and do some calculations. And of course, if I do it like that, if I say cout s plus 100 end line, we're not going to do the calculation. If I press F6 here for, actually, oh, I forgot a semicolon here. Actually, yeah, you can see mismatched types. We have integer and a container iterator, which is essentially the string. So it's not possible to add the string to a number here. We cannot do calculations with this value here. In order to do that, in order to be able to do that, we need to typecast the string into an integer. And for this, we have more than just one way. For example, if you're using, for some reason, something below C++11, you need to use the string stream. This is the S stream library. I'm not going to show that way because I assume that almost everyone is using C++11 or above. And in that case, we have the stoi function, the string to integer function, s2i function. And that's very simple, very self-explanatory. The only thing that we do is we say int I equals, and then we need to use, actually, I don't know if we need to import something for that. I don't think we need to import anything. I think we should just be able to use stoi here, string to integer, and then we pass s, and then we cout I plus 100 end line. And if I'm not mistaken, this should be sufficient. Yeah, as you can see, we converted using this function here, s to I. We converted the string to an integer. Now we need that function because the string is not a primitive data type. This string here is not a primitive data type. For other data types, we don't do it like that. We don't need a separate function. What we do is we just use the basic typecasting, and this is done like that. We specify in parentheses the data type, for example, integer, and then the value. So in this case, we're typecasting 10.92 into an integer. And you might ask, when is this necessary? When is this useful? And this is useful, for example, let's say we have a float f, and this float is 10.78. And, you know, if you save that float directly into an integer, it's going to typecast it automatically. So you would not need the typecasting operation. You would not need to perform it manually. So if I say int I equals f, and then I cout I, you're going to see that it's going to cut off the decimal places automatically. We don't need to specify anything here, as you can see. But sometimes you might not want to save this into an integer, but you just want to output an integer or use an integer. For example, if I add this to an integer and I don't want to deal with a float here, or I don't want to deal with the decimal places here, but I also don't want to store it into an integer so that it's typecasted automatically, what I do is I say int f, and then either just int f, we can do it like that, and you're going to see it's going to just output 10, or we can also work with this result and say plus 90 for example, and in the result you get 100 without the decimal places. If I don't do this, the whole expression is going to be a float, and we're going to get a floating point number, as you can see. So this is how you do basic typecasting. And of course, it also works the other way around. Let's say we have an integer int I equals, I don't know, 7, or actually let's say int a equals 7 and b equals 3. And if we divide 7 by 3, of course, we don't get another integer. But if I do this here and I say int a divided by b, what I get is I get 2, because, or actually what happens here, semicolon, never forget the semicolon. What we get here is 2, an integer result, even though that 7 divided by 3 is not an integer result, but since we're dealing with integers, we cannot represent floats as a result. So what we can do here is we can typecast those into floats. So we can say float a, float b, And for this, we don't need to store them because, again, if we store an integer into a float, it's going to be converted automatically. But in this case, we can do it manually, and you can see that the result is 2.333. So this is how you typecast an integer into a float or a float into an integer. So this way of typecasting works perfectly fine when we're dealing with simple primitive data types like booleans, characters, floats, doubles, integers, and so on. But as we saw, it doesn't work with strings. So we cannot just go ahead and say int string or int some text. You can also not go ahead and do it the other way around. You cannot just go ahead and say string and some integer. It doesn't work like that. If we want to do it that way, what we need to do is we need to say int I equals 10, for example. And in order to get that integer and convert it into a string for whatever reason, we need to say string s equals, or actually I'm not even sure if it's not possible to just do it like that. We're improvising right now. Let's see if it works. I don't think that it's going to work, to be honest. Yeah, it doesn't work. So if you want to turn this integer here into a string, if you want to save it into a string, what you do is you say std to string, and this function, to this function you pass an integer. So you call the std namespace, you refer to the std namespace, and then you call the function toString, you pass an integer, and what you get as a result is a string. So we can go ahead and run this, and you can see that it gets, we get 10 as an output here. Now, of course, we can also directly print I. It's not like we need to have a string for this one. But actually, what you can do when you have two strings, of course, is you can append them. So let's say you have another string. Let's say this is string 2, and let's say we have string s1. And this string says something like this number is. What we can do then is we can add them. We can add those two strings together. We can append them onto each other. So we can append s2 onto s1 by just saying s1 plus s2. And as we saw, if we typecast both into integers, we can do an arithmetic operation. We can just do the addition, the arithmetic mathematical addition. And if we turn both into strings, we can append them, because strings are just lists of characters, sequences of characters, or as the name says, strings of characters. So if we do it like that, we get this number is 10. So this is how you typecast an integer to a string. Now, storage classes are probably the first topic that we're talking about that you're probably not going to encounter in Python, in Java, and C#. Because it's a little bit more low level, we're talking about memory management here, manual memory management, and this is done to optimize performance. And since this is not a very advanced topic, yes, it's new to everyone who's watching, who's not coding in C, C++, Rust, or something like that. It's a new topic, but it's not very complicated, and we're going to talk about the storage classes since they are somewhat related to working with variables and data types and so on. And we have 6 storage classes. We're going to talk about 4 of those in a little bit more detail, and we're going to just mention 2 of them for the sake of completeness here. The first one that we're going to talk about is the auto storage class, and actually it's the default storage class. So when you use the keyword auto, you're actually doing the same thing that you're doing when you're not using a keyword at all. So automatic storage duration means that the compiler figures out itself how long a variable should be stored. And this is the default thing. So if you just say int a equals 10, this storage class is already auto, so automatic storage duration. However, what you can do with auto that you cannot do with the normal way of declaring variables is you can make the data type automatic. So you can say auto a equals 10, and the compiler is going to figure out that this has to be an integer. Now, don't confuse this with dynamic typing. C++ is statically typed. It's not dynamically typed like Python. The compiler will figure out that this is an integer. So it's going to be a statically typed integer. You cannot just go ahead and make this dynamically typed here. It's just that you don't have to specify it. This, of course, slightly increases the compiler time, but it's not negligible. It's not something that you need to worry about too much. But if you want to choose the auto keyword in order to not specify the data type yourself, the compiler is going to do it for you. You don't need to worry about that, but except for that, you don't have any differences than just saying int a equals 10. It's the same thing because the auto storage class is actually the same as not specifying a storage class at all. All right, so the second storage class that we're going to talk about is called extern, like that, extern int e. And what this does is it tells the compiler that there is this integer e, which is global, it's accessible from multiple files, it's public, global, whatever. And how this works is that you have one file, we're talking about multiple files here, otherwise this storage class doesn't make a lot of sense. And I know we haven't talked about header files yet, but the idea is that you have somewhere you define this integer e. Let's say in this file you define it not with the extern keyword, but just integer e, and then you do something with it like e equals 10 or whatever. And then in another file, let's say this down here is another file, you would say extern int e. And by doing that, every other file that includes that file where this is written has now access to e, which is defined here. So this essentially tells the compiler that, or it says there exists some integer e that's globally accessible. So it specifies the existence, it declares the existence. The compiler doesn't care about where this integer e is defined. It just cares about that it is defined, and we know that it's globally accessible, so we can work with it throughout different files, and this extern keyword specifies exactly that. So when we say extern int e, we cannot define it, so you cannot do something like extern int e equals 10, because extern int e just specifies there is somewhere this integer e, and it's globally accessible, and you can use it in this file and in every file that includes this file. This is just specifying that there is this integer e out there somewhere, and we can use it here. So we can say cout e, for example. Of course, we need to use namespace std and so on. But this is how it works. You say there is this integer e somewhere, and I can use it in this file here. So for the next storage class, we're going to get a little bit more technical. The storage class is called static, like static int a equals 10. And it has to do with memory allocation and with scope. And if you've never programmed before, you probably don't know what scope is. If you've programmed in Python, Java, or C#, you probably know what scope is already. It's essentially just an area of, you could say, accessibility. Let's say, for example, I define int a equals 10 here. This is the scope where a is defined. This is the scope here. The main function is the scope. I have this these curly brackets here. And if I say int a equals 10, this is the scope of that variable. Now, I know we haven't talked about functions yet, but I'm going to just give you a quick example here. Let's say we have another function here, int my function, that does something. We're not going to care about the function signature or something like that in detail. But here I can also define a variable. Let's say I have int b equals 20. Now, because of the scope of a is defined for the main function, I cannot access a in here. I cannot say cout a. Now, even if I say, of course, using namespace std, not best practice, remember, I cannot go ahead and say cout a, because a is not defined in that particular scope here. In the same way, I cannot use b in the main function because b is defined in that scope here. Whereas if I say something like int c equals 30 here, I can access c in here, and I can access c in here because the scope of c is the whole file here. Now, again, we're not going to talk too much about functions, but the idea of the static storage class is that or actually, let's talk about what happens if we don't use the static storage class. Whenever you define a variable like int b equals 10, what the program does during runtime is it allocates the memory for b, and then it does something. So this function does something. And in the end, we're done with the function. We return a value here, like return 0, for example. And this function is done. And what we do is we get back to main. We get out of the function scope here. And what we usually do is we free the memory that was allocated for b. So b allocates memory, does something, and once it's out of scope, it's deleted again. We free the memory, we don't need the memory anymore. The block is freed, and next time we get into my function, we need to allocate it again. So let's say I call my function multiple times. What happens is I allocate memory for b, I do something with it, and then once I get out of the function, I free this memory, I delete b. And then next time again, I allocate, I free, I allocate, I free, and so on. Now, if we do that, if we don't want to do that, if we want to have a static allocation, if we want to have the allocation being valid until the whole program is terminated, what we can do is we can say static. So static int a equals 10, for example. Now in this case, this would be useless because the main function is all there is. So essentially the scope doesn't end until the whole program terminates. But if we define static int a in another function, let's say in my function that we wrote down below a couple of seconds ago, if we do it there, this means that once we get to that point, once we get to the point that a is allocated, it's not going to be freed until the program terminates. This is what the static keyword does. It allocates the memory for a, and it doesn't free that memory even if we get out of scope, which means that next time when we get in scope or inside of scope, next time we call that function, the memory for a is already allocated and doesn't need to be allocated again. It's already there. And because of that, this can increase performance. Of course, it doesn't free the memory, so it's, you could say, uselessly allocated. It's allocated even though you don't need it, so you're taking up more space in a sense, but because of that, you don't need to reallocate it once you need it again. So if you know that you're going to use a function frequently and you're going to use a certain variable frequently and you don't want to reallocate it every time it gets out of scope, or actually you don't want to free it when it gets out of scope and you don't want to reallocate it once you get inside of scope again. If you want to have this allocated all the time in order to save that that runtime that you're using to allocate the memory, you can use a static storage class in order to do that. And this can sometimes increase performance. So for the next storage class, we're going to look at how variables are actually stored when we define them. Let's say we say int a equals 10. What is happening here? Now, first of all, we look at the data type and we know we need 4 bytes for an integer. So what we do is we go into the RAM and we allocate a block, a memory block that has 4 bytes, and we save the value, or we store the value 10 inside of that block, inside of those 4 bytes. Now, whenever I say something like a plus equals 10, what happens is the CPU goes to the RAM, gets the value from that memory block, applies the arithmetic operation, and then stores that value back into the RAM. And the RAM is a very fast memory. It's very efficient, so it's very fast. But still, sometimes you might want to have the actual variable closer to the CPU. It's not always possible, but sometimes a variable is going, or an object is going to be accessed very, very often, and you want to have it close to the CPU and not save it in the RAM, but you want to save it in one of the registers of the CPU. And if you want to do that, you can use the register keyword. Register int I equals 10, for example. In this case, if it's possible, only if it's possible, we're going to store that int I into a register rather than the RAM. Now, what do I mean by if it's possible? This means that sometimes, of course, we don't have free registers. The RAM is quite big nowadays, so we have a lot of space there. We're not likely to run out of RAM unless, you know, we're programming a giant application. But usually you'll always have some space in the RAM. However, you're not always going to find a free register. And if you don't find a free register, what's going to happen is you're going to allocate normal RAM memory. So you're just going to access the RAM again. You're going to allocate a block of memory inside of the RAM instead of a register. But if a register is free, so this is not a guarantee that you're going to save this variable in or this object inside of a register. It only says if there is a free register, yes, I'm going to use it. I'm going to allocate, I'm going to store the object or the variable inside of that register instead of the RAM. And because of that, the access to that variable is going to be way faster because it's actually in the CPU. You don't have to go the way, or the CPU doesn't have to go the way to the RAM to access it, to process it, and then to store it back into the RAM. It's actually in the CPU already, in the registers of the CPU. So this is again something that you can use to increase performance. Of course, however, don't abuse this, quote unquote. I mean, abuse is probably not the right word here, but don't overuse this. Don't store everything in a register just because you think that's going to make your program faster. You want to select very few objects or variables that you're going to store in the register because they're going to be accessed faster than the ordinary variables or objects that are stored in the RAM. So if you know that something is going to be used very, very often, very frequently, you might want to store it in a register instead of the RAM. But of course, don't overuse this. Now, one thing that you need to know here, if you are going to use a register storage class, is that you cannot use pointers. And I know we haven't talked about pointers yet, and you probably don't know what pointers are if you've never coded in C, C++, Go, Rust, or something like that. But essentially, a pointer is just something, an object, let's say, that points to a memory address. And of course, if the object is not stored in the RAM, but in the register, it doesn't have a memory address of the RAM. So I'm going to show you real quickly what it's going to do. We're not going to talk about pointers yet. We're going to have a special video on pointers, but essentially I'm going to show you that like that, you can access the memory address of an object here. And probably we're not going to see the register here because the register is not always free. Actually, it's pretty unlikely to have a free register. And because of that, we can see a memory address here. This is the RAM memory address. So in this case, we didn't store it in a register. We stored it in a normal memory block in the RAM because there was no free register. If there was a free register, we would not be able to do this. We would not be able to see a memory address here. We would see something like register. I'm not actually sure what we get here. I'm also not sure if we can use a size of operator, but I think we should be able to do it. But the fact is, if you successfully store an object or a variable inside of a register, you're not able to access it with pointers. You cannot point to its memory address because it doesn't have an address, it has a register. It's a register for this variable. So this is something that you can do to increase the performance of your program even more. So last but not least, for the sake of completeness, we're also going to mention the other two storage classes as well. We're not going to talk too much about them, just mention that they exist. And the first one is called mutable, and it has to do with constants and classes, and it's not important yet because we've not reached object-oriented programming yet. And the second one is called thread local, and it's something that was introduced with C++11, I think. And this is also something that we're not going to talk about yet because it has to do with threads. Again, just wanted to mention them for the sake of completeness. We also have mutable and thread local. So I think in the fifth video of the tutorial series here, we talked about comparison operators and their Boolean results. And we also mentioned that they are going to be very important when we get to conditions and loops. And now we're getting to conditions, which are essentially just if statements. So if you're already familiar with programming, you know what if statements are. Actually, if you're programming in Java or C#, you actually know how to write if statements, if else statements in C++ because the syntax is the exact same. So if you know how to write if else in Java, you know how to write it in C++. If you know it in Python, it's a little bit differently, but it's essentially pretty similar. So if you understand it in Python, you can also understand it in C++. And the only thing that you need to learn are the syntactical differences here. Whereas if you have never coded, if you don't know about if-else statements at all, I'm going to explain it from scratch here as well. And the idea is that up until now, we had in a function a couple of statements. And yes, by the way, you saw right, I'm using namespace std. Because by now you should already know that this is not the best practice way, so we can do it for the sake of simplicity. However, of course, if you're working in a project, don't do it like that. It's not considered best practice. However, what we did in the main function is we always executed some stuff like cout something, end line, then we created variables and so on, and everything was executed step by step. So we said cout, define something, add something, do something, and then sooner or later we get to the end, return 0. Now, this is not very conditional, and as the name already says, conditions make our code more conditional. It's less linear. And this means that we have certain conditions for executing certain statements. And those conditions are specified with the so-called if statement. So we say if, and then in parentheses, we specify what has to be true in order for a certain block to be executed. For example, let's say we have a variable int a, and we input a, so we get user input for a, like that, and then we say, okay, if the input that we have just given to the program here, if this input is larger than 10, then we're opening up a new block here. By the way, this is also a new scope, so if we define a variable in here, it's not necessarily going to be, we're not going to be able to access it from the outside here, so this is a block of code here. And in here we can do something, I don't know, cout your number is larger than 10, a very simple message. And then, so this block right here, if we just leave it like that, what happens is we say if a equals 10, not equals 10, sorry, is larger than 10, greater than 10, if that is the case, if this comparison here returns true, that block is going to be executed. Otherwise, it's just not going to be executed. So right now we can see if I compile this program here, we can see I can enter a number, let's say 9 in this case, and nothing happens. We just get 9, we input 9 and nothing happens. Whereas if I run this again and enter 99, for example, it says your number is larger than 10. So as you can see, depending on the input, this block gets executed or not. And if we want to also specify what happens if this condition is not true, we can use an else statement as well. So we say if a is larger than 10, then do this. Otherwise, if this is not the case, so else, and we open up a new block here, if this is not the case, we say else cout your number is not larger than 10. You can also write is less or equal to 10. So we can go ahead and run this again. And you're going to see that we have 7 and it says your number is not larger than 10. If I say 99, your number is larger than 10. If I say 10, it's going to say your number is not larger than 10 or greater than 10. I think greater than 10 is actually the term that we want to use here. I'm not sure if larger is correct here. Yeah. So what you can see here is that we have certain conditions and certain pieces of code that get executed based on that condition. Now, what do we do, however, if we want to check for multiple conditions? So let's say I want to check if a is larger than, or actually let's change this to 100 here. I want to know if a is greater than 100, and if it's not greater than 100, I want to know if it's at least greater than, greater than 50. So if this is not the case, I want to know if it's greater than 50. And if it's neither greater than 100 nor greater than 50, I want to print something else. And in this case, I can go ahead into the else branch here and formulate another if statement. So I can say, okay, if it's not larger than 100, I can say if, so inside of the else branch here, I say if a is greater than 50. If that is the case, we can get this out in here and say your number is not greater than 100, but greater than 50. And then we can add another else branch here and say if even that is not true, we can say cout your number is not greater than 50. End line. So this is a very trivial example, but we can compile it and enter something like 70. And you can see your number is not greater than 100, but greater than 50. We can do the same thing with 120. Your number is greater than 100. Then we can say 40. Your number is not greater than 50. If I say 50, not greater than 50. If I say 100, it's not greater than 100, but greater than 50. So as you can see, we can do it like that, but we can also do it in a different way. We can use something called else if, which is essentially the same thing or a very similar thing, but it's written differently. We can say else if in one line here, else if a is greater than 50, then do something. So in this case, come on, I'm going to just simply print greater than 50. And then I can still append one else branch to those. So here I can say less or equal to 50. And if we run this here, we're going to see that we have the same functionality. So 66, for example, is greater than 50. 12 is less or equal to 50. And 190 is greater than 100. So you can also write it like that. So the switch case statement is just an additional decision-making structure in C++. So in the last video, we talked about if, else, and what happens when we do if-else statements. So first of all, we have if, then some condition in the parentheses above. And if that condition is true, so it's a Boolean value in the end. So whatever we write in there, a comparison, a function, whatever it is, if it returns a Boolean value, it can be put into that into those parentheses there. If the return value of that is true, we're going to execute this block of code here. Otherwise, we're going to go into the else block. And of course, we can also have else if with other conditions and so on. We already talked about that in the last video. And now we're going to introduce switch case statements. And for those of you who only code in Python or have only coded in Python, you probably don't know about switch case statements because they're not supported in Python. And how they work is you have to pass either an integer or a character, so a char, to that switch case structure, and then you can define cases for the value. So let me show you what I mean by that. Let's say we have some integer, I don't know, x, and it has a certain value, or actually let's say it's a user input. What we can then do is we can say switch x, and then we can just specify certain cases. For example, one case could be x is 8. And if x is 8, we use a colon here, and we use indentation here. If the case 8 happens, so if the case 8 is the case that we have right now, so if the value of x is 8, then we can do something. For example, I don't know, cout the value was 8 or something. And then we can break. So we always need to end a case with a break, because otherwise, if we don't end the case with a break, it's just going to continue into the next case. And we can specify a bunch of cases here, like 10, for example, and we can say something else here. I don't know, do the action for input 10. Just have to define whatever we want to do here. And when we're done with the code, we specify a break statement again. And then we can also specify a so-called default statement, which is essentially if the input was not 8 and was not 10 and not one of the other case options that we can define here, we're going to go to the default value, which is something like everything else essentially. And we can define an action here, stuff like invalid input, for example. And then we can break this as well. So now when we run this, you can see what this does. And we can enter something like 0, for example. It says invalid input. We can enter 8, and we get the value is 8. And we can also enter 10, do the action for input 10. Now in this case, this is not really useful. So we're going to change this right now into a simple calculator. We're going to build a simple calculator here. We're going to say int n1 and 2 for number 1, number 2. And then we are going to say character operator. And now we're going to say cout, enter the first number. And this is it. Then we're going to say enter the second number. And in between, we're going to say choose an arithmetic operation. And of course, we're going to ask for the inputs respectively. There you go. And then we can go ahead and say switch, and we can pass the operators. So switch OP, case 1, the operator that was specified is the addition operator. If that is the case, we're going to return n1 plus n2. Break. And we can now copy this here for all the individual operators. So we can say for minus, for subtraction, for multiplication, for division, and last but not least, then also for the modulus operator, so for the remainder. And don't confuse this with a percentage operation, by the way. And otherwise, if we get something else than those 5 operators, we're going to say operator not supported. There you go. Break. All right. So this is the full structure here, and it should work already. So let's try it. Enter the first number. Let's say I want to say 22 times 88. And this is the result. Then let's do something else. Let's say 6 modulus or modulo 4. We get 2 as a result. Then I can say 88 divided by 5. And of course, maybe it makes a little bit more sense to make this a float so that we can do division properly. Let's recompile this. What do we have here? Oh, okay, we cannot use the modulus operation here, but we can typecast this into an integer here if we're calling the modulus operation, and then it should work. So now I can go ahead and say 88 divided by 7, for example. Oh, sorry, this was not the right thing. 88 divided by 7. And you can see that we get a floating point result. At the same time, I can do the modulus operation. So I can say 17 modulus 3, and I get 2. And I can also go ahead and say 17.65 modulus 3.89. But what's actually happening, since I'm typecasting, is 17 modulus 3. So I'm getting the same result here. As you can see, this is how you can do a simple calculator. And of course, you can do this with if-else statements as well. So you can just say if operator equals plus, then do this. Otherwise, else if it equals this. But this is just more convenient. For the switch variable, you can only use characters and integers. You cannot use anything else. You cannot use floats, doubles, or more complex objects or structures. But as you can see, this is a way more convenient way to go through the different options. All right, so loops are just basic programming structures that allow us to execute the same block of code repeatedly, either as long as a certain condition is met or a specific amount of times. We have different types of loops for that. We have 2 major different types and a third different type, which is actually just a slight variation of the first one. And the first one that we're going to talk about is the while loop, and it's initialized with the keyword while followed by a condition. We already know what conditions are: expressions that result in a Boolean value, so either true or false. This can be a Boolean value itself, so either true or false. This can be a function that returns a Boolean. This can be a comparison, whatever we want, as long as it results in a Boolean. It is a condition. It can be stated inside of those parentheses here. And as long as this condition inside of those parentheses returns true, we're going to execute this code over and over and over again. So in this case, this would go on forever. This would never stop, because while true, obviously true is always true. It's not going to change. It's a constant, a Boolean constant. We're going to execute the code here over and over and over again. But we can also go ahead with a slightly different example here. We can go ahead and say int I, and then we can say std cin I, so we're getting the user input, saving it into I. And then what we can do is we can say while I is larger than 0, greater than 0, we're going to say std cout I, and then we're going to decrease I by 1. So we're going to say, or actually we can go ahead and do this directly in here. So we can say I minus minus. Notice again that I minus minus means that we're printing I as it is, and then we're decreasing it by 1, not the other way around. So we're not doing this, we're doing I minus minus. And essentially what this does is the user inputs a number, and as long as this number is positive, we're decreasing it and printing the value. So we're doing some sort of countdown here. By the way, I need to turn off my antivirus system, because otherwise whenever I compile C++ code, it's turning on. I don't know why. Then we can go ahead, compile this, and I can input a number here. Let's say I go with 8, and as you can see, it says 8, 7, 6, 5, 4, 3, 2, 1. We could also go ahead to 0 if we want. So we can either go ahead and print, if we don't want to decrease it further, but we want to print the value when it reaches 0, we can go ahead and say cout I at the end again. Because if you just go ahead and say larger or equal to 0, you can print 0, but it's going to end up as minus 1, as negative 1. So in this case, it will still be 0 in the end, but it will also be printed. So we can go ahead now with 30, and you can see it does the full countdown up until 0, or down until 0. So this is the basic while loop, how it works. Now, before we get to the second major type of loop, we're going to cover a slight variation of the while loop, and this is the so-called do while loop. So in this case, we say do, specify the block of code, the loop code essentially, and then we add a while in the end. So we do it like that, and we can do the same thing actually. And the difference here is that we check for the condition after the first iteration. So this means that no matter what the condition is, we're going to execute this block of code at least once. So in this case, we can do the same thing. We can say std cout I minus minus std endline. And this code will be executed here even if we start with a number that is below 0. which otherwise would not happen in an ordinary while loop because the condition gets checked immediately and you don't even enter the loop if the condition is not true. In this case, we do it at least once, and then if the condition is still met, we can do it as long as the condition is met. But we're going to do it at least once. This is the do while loop, and we can check it out. So I can go ahead first and enter a valid number like 10, and you can see it works like the while loop. But now if I go ahead and enter something like -9, you can see that it prints -9 at least once. It also decreases it. We can check that this is true by just printing the value of I in the end. So you can see that it's still, or not still, actually it's going to be -10 if I enter -9, as you can see. But it doesn't continue, or it doesn't repeat the code over and over again. It does it one time because it has to do it one time, even if that condition is false. We can check that by saying while false. So even if the condition is definitely false, 100% false, it's going to execute this code at least once, no matter what I put in. So 10, it's going to say 10. And then afterwards 9, because it's decreased, of course. So this is the difference. If we do a while loop, we're going to check for the condition immediately. A do while loop, we're going to execute the code once, and after that, we're going to check for the condition. So you can imagine it to be like doing this for sure one time, and then we can start with a new ordinary while loop. This is the same thing. So the second major loop type that we're going to look at is called the for loop, and it's initialized with the keyword for, followed by parentheses, the loop head, or header, so to say. Then we have the block of code where we do something. And inside of the head, or the header of the for loop, what we specify are three things. First of all, a control variable. This can be a variable that was defined in the program before, so we can say int I here, and we just have to initialize it here, saying I equals 10 or something like that. Or we can say int I directly in there. So we can go ahead here and say int I equals 0. The second thing that we specify after the semicolon here, we specify a condition which says do this or execute this block of code as long as this condition is met. So this is something that we already know from the while loop. Stuff like, or something like I is less than 100. And then an action that is happening with each iteration. So something like I++. In this case, what we do is we create a variable starting at 0. And as long as this variable is below 100, we're increasing it by 1 and executing the code inside of this loop here. So for example, we could just go ahead and say std_cout hello. And what this will do is it will print hello 100 times. Like that. We can go ahead and see what happens. You can see it prints hello 100 times. We can also go ahead and print I, of course, because I is a variable that is, if we define it here like that, int I equals 0, it's valid or accessible in the scope of that loop. Of course, we cannot access I here, so this is not valid. We cannot find a variable I in here. It only exists in the loop, which is also the reason why we can define it here again. So this is not a violation of any rules. And if we do that, we can see it's the same thing like counting. We can also start at 100, for example, and say as long as it's larger than 100, we're going to decrease it by 1. And then it's more like a countdown. What's happening here? Why didn't it work? It's 100 less than, oh, greater than 0. Sorry, not greater than 100. And then it works like a countdown, as you can see. So the major difference here is that we specify in the for loop more in the header. It's more used for counting and iterating. So when we get to collections, to lists, to arrays, and so on, we're going to use more for loops, whereas while loops are actually, if you want to do something like as long as I don't get a trigger, as long as some boolean is not true or not false actually, as long as something is met, let me do this. If you want to have that kind of loop, you're going to use a while loop. And if you want to count, if you want to iterate, if you want to do something a certain amount of times, you're going to use the for loop. All right, so functions are essentially just blocks of reusable code. And we already know such a function, which is the main function. It's written like int main parentheses, curly brackets, and a return statement. And we've talked a little bit about that, but now let's get let's get into more detail here. So the first thing that we do is we specify a return value data type. In this case, it's integer, and this return value data type is the data type that we demand from the return statement. So in this case, we return 0. 0 is an integer. The return value type of the function is integer, so that's okay. And essentially what this means is that, let's say I have another function down here called add, for example. It's also of the data type int. And I have parameters in here. Or actually, let's for now just not use any parameters at all. Let's just say I have a return value 10, for example. Now, if I call add in main, and it would not work in that constellation, we're going to talk about that in a second, but let's say the function add exists and I call it in main. What happens is that as soon as I call add here, I jump into that block of code, execute the code lines here. Of course, I can have multiple code lines with statements. And then what happens is once I'm done, I reach the return statement, which means that I return to the point where this function was called, in this case, this point here, with the value 10. With the value 10 meaning that I can get the value and store it or process it, which means that I can go ahead and say int, x equals add. This is important because return means that I can always get a value from it. So again, we call the function, we get inside of it, we execute the function code, we return to the point where the function was called with the value that we return. And this value has to have the data type that is specified here. This is how functions basically work. And we can actually go ahead and implement a real add function here. We're going to specify two parameters. So inside of these parentheses here, we can specify parameters that are going to be processed by the function. I mean, they don't have to be processed by the function, but usually when you pass something, you don't want to pass it uselessly. So we're going to say int x and int y. Now, those are not actual variables. Those are just definitions. We say, okay, this function takes on an integer, which we're going to refer to as x, and an integer that we're going to refer to as y. And then inside of that function, inside of the function scope here, we can work with x and y. In this case, the only thing we want to do is we want to return the sum of those, so x plus y. This is all we want to do. And this function right here, what it does is it takes integer x, integer y, it just adds them, and then when we return it, we jump back to the point where this function was called and we return the result. In this case, just the sum of the two parameters. Now, we're not going to see that working here because even though Visual Studio Code is going to show us that this function exists and we can actually call it, we're not going to be able to do it, and I'm going to tell you why in a second, but first of all, let me show you. std cout at 10 and 20, for example, std end line. So if I run this right now, you're going to see that we get error. Add was not declared in scope, in this scope essentially. This is because in C++, in order to be able to access a function, you need to have already declared it above it. So we're going top down here. We're going, if a function is defined here, like the int function, the int main function, not the int function, the int main function, we know that this function exists down here, but we don't know that the function that is defined down here exists here. We don't know it here. So what we can do to fix it is we can just go ahead and put the function above the main function, then it's going to work. Because first we define it, then we use it. Obviously, that's the logical order. But this is not necessarily a good practice. I mean, you can do it, but sometimes it's not a good practice. And usually what we do is we define the main function first, and the implementation of the other functions comes below that main function if it's in the same file at all. But that's not the only problem. It's also a problem when we have, for some reason, other functions here. So let's say I have a function f1 that does something, I don't know, return 0 in this case. You know, I'm just going to do some sample functions here. It doesn't matter what these functions are doing, but let's say somewhere inside of that function, f1 needs to access in some if statement, in some loop, somewhere in here, we need to call f2. But at the same time, in some if statement, in some loop, in some corner of that function f2, we also need to call f1. So what do? Do we define f1 first? Do we define f2 first? Because obviously f1 refers to f2 and f2 refers to f1. So we cannot have both functions above the other one. Or can we? Because that's actually what we need to do here in order to have that happen. What we can do, or what we usually do in C++, is we go ahead and define the functions up here, but we implement them down below. So what we do essentially is we say there is a function with a return type int that is called add and takes 2 integers as a parameter. We don't need to specify x and y here. We can do it. It's not wrong. But it's enough to just specify that we have 2 integers. Now this is the function signature. This is called the function signature, where we have the return value, the name, and the parameter data types, and also the amount of, obviously. By doing that, we tell the whole program here that there is such a function, so you can use it, but it's going to be defined later on. Because of that, the main function now knows that the add function exists. It knows that it can pass 2 integers, and it's going to get an integer so it can use it without giving us an error at compile time. But at the same time, we also have the implementation down here. So I can go ahead and run this, and you're going to see that it still works, even though add, the functionality of add, is defined below the main function. And I'm not going to do this really here. I'm not going to implement it actually here because obviously, if I just make function 1 calling function 2 calling function 1, and so on, it's going to never stop, or it's going to just do nothing. But essentially, if you have a reasonable or 2 reasonable functions that call each other in some cases, this is going to be necessary, and you can just go ahead and say int f1, int f2. So you're just defining that those functions exist, and that's it. And then down here, you define what they're doing actually. Now, actually, we don't need to always return an integer, even though we did it up until now. We can also return a float, a boolean. For example, I don't know, let's say we have a function boolean is greater than. We can do it like that. We can say is greater than, and then we pass a number x and a number y. And we return if the number x is greater than the number y. So we can go ahead and say std cout is greater than 10.5. We should get a 1 here. And of course I need to define that that function exists. So bool is greater than, that takes 2 integers. And we can go ahead and run this now. I can see I get a 1, which stands for true. What we can also do is we don't have to actually return any data type at all. Right now we are returning integers, booleans. We can do it with float, but sometimes we just don't want to return anything at all. And you don't have to return something in C++. Actually, it allows you to define an integer function here and not have any return statement, or just return nothing. But it's not something that you should do. So what you should do is, if you have a return value type, you should actually return something. If you don't have one, or if you don't want to have one, you can go ahead and define a void function. And this void function is, void means empty or nothingness or whatever. And void essentially says that you don't have any return value at all. And you can do it like that. You can say my function, for example, void my function. And you're going to just do something in here like print hello world, like that. So this does something, but it doesn't return something. And because of that, we can just call it my function void my function. And if we run this, we can see it gives us hello world. Now, of course, the return value of that function is non-existent. So we can go ahead and say std cout what this function returns. And it's not going to return anything, actually. It's going to return the void, nothingness, which essentially gives us an exception. I did not know that we're going to get an exception here. But all in all, when you have a void function, you don't want to have a return value anyway. So you're not going to return anything using a void function. Now, one thing that at least we learned in university that is best practice or done, or you should be doing, is when you have 0 parameters, when you don't have any parameters, you should not just not have any parameters, but you should pass a void keyword in here. I'm not sure if this is really something that is done amongst professional, professionals. We did it in university. That's why I'm showing it to you, but take it with a grain of salt. I'm not sure if this is the best practice actually, but you can just go ahead and type void in here to make clear there are no parameters for those functions. So we do it like that. Down here, you can do it as well. This essentially has the same effect as not passing any parameters at all. It just means emptiness. We don't have any parameters. It's maybe just an additional safety to say nothing is going to be in those parentheses. All right, so now we're going to talk about something called overloading functions or function overloading. And the basic idea is that we have a function like int add here that takes 2 integers as a parameter and has this signature int add with 2 parameters int. And maybe you want to have another function called int add that takes 3 integers. Now, this is possible in C++, and it's called function overloading because essentially you're using the same name. I think this is not possible in Python as far as I know. I'm pretty sure it's not possible in Python. You cannot define the same function signature, or not the same function signature, the same function name with a different function signature and have it be a different function. So in this case, we have int xy, which returns x plus y, and here we can say x plus y plus z. But in this case, we're also going to print something just to see that it's a totally different function here. We're going to say using 3 parameters, std, and line, like that. And of course, we need to define the header or the signature up here. Int. And then we can go ahead and print how we also add 30 to it. And by doing that, we call a different function. We call the function this function here and not this function here with just more parameters, because this is not, we're not talking about functions with a variable amount of parameters yet. We're just talking about a fixed size of parameters or a fixed function signature, but we have the same function name for different signatures. For example, we could also have a string add function. I don't know if we have some idea of how to process that, or if we want to do something with that. In this case, you can see it's calling using 3 parameters because we're calling this function here. We're not calling this function with just more parameters. And we can also go ahead and say int, or actually, sorry, string std string add std string s1 std string s2, and we can return just on a concatenated version. I'm not sure if it's done like that or if it's possible like that, but I think it is actually. So by doing that, of course, we need to say std string add std string, which is a class, by the way. This is not a primitive data type. We're going to talk about object-oriented programming in a future video. But for now, we're just going to print the result of hello and world. Let's see what happens, if it works or not. Yeah, as you can see, it works. And this is, again, another function signature. One thing that I'm not sure about, to be honest, is if we can have the same, or actually I think it's not possible, but let's find out. If I have the same return value, actually a different return value. For example, I'm returning a string here, but I have the same parameter signature, so int, for example. I think this should not be possible because when I'm calling it, I don't know what it should be doing right now. We don't know, should it be returning a string or should it be returning an integer? So my guess is, I'm not sure, we're going to find out now. I'm not sure if it's going to actually be possible to compile that, but we're going to do it, or we're going to try it. We just need to return a string. And we're going to say, I don't know, this is just a test. So we're going to return test. But I think we should get an error here. Yeah, as you can see, unused, or actually this is a warning. Where's the error? Ambiguating new declaration of that. Yeah, as you can see, it's confusing because when we call add on 2 integers, what should it do? Should it return a string or an integer? So it doesn't work like that. In order to overload functions, what you need to do is you need to change this part. This part needs to be different. You either want to have a different name or a different set of parameters. So this is how you overload functions in C++. Now, one thing that I also want to talk about is default values for parameters. Let's say we have something like the add function here with 3 parameters. And what we want to do is we want to have a default value for z, for example. So if someone does not pass the value for z, or actually then it's going to be that. So let's, or actually this, so let's comment that out. Let's say we don't have that function here. We don't have it, doesn't exist. We just have it with 3 parameters here, but we want to have the option of just passing 2 and the third one being chosen automatically if it's not passed. So what we can do here is we can just go ahead in the function signature up here and say the third int equals to 90, for example, like that. So you can see int add int int, and the last int is equal to 90. So in this case, what we get here, since we don't have the function with 2 parameters anymore, it does not exist anymore, we're calling the function with 3 parameters, but since we're not passing a third one, it's going to assume that it's just 90. And in this case, we're passing 1, so it's going to assume it's 30. So you can think about this. 10 plus 20 is 30, plus 90 is 120. In this case, we're going to get 120. And in the third one, in the second function here, in the second function call here, we're going to get 60 because it's 10 plus 20 plus 30. So let's see what happens. And you can see 120 and 60. And if we don't do this here, this function call would not even be possible. So we can see that we run into an error because there is no matching function to add int int because we commented out. It doesn't exist anymore. I mean, actually, this function, technically speaking, exists, but we define it down here. So it does not really exist for the main function. But as you can see, this is how you define default parameters. And you can not only define it for one, you can define it for multiple parameters at once. So you can say, okay, if I don't pass anything, this is 90. And if I don't pass anything for the second one, it's going to be 50. And then, if you pass something, it just takes the values you passed. But if you don't pass anything, we can also just go ahead and say add 10. And then we're going to get 50 plus 90 plus 10 is 150. So in this case, we should get 150, as you can see. Now, one thing that you need to notice here is that you have to do it from right to left. So if you want to have a default value for this one, for the second parameter, you also need to have one for the third parameter. You cannot do it like that. You cannot say the first parameter has no default value, the second one has one, and the third one doesn't have one again. This does not work. I think it should not be even able to compile. As you can see, default argument missing for parameter 3. It doesn't work like that. And of course it makes sense because how do you want to determine what you passed and what you didn't pass? If I pass 2 parameters, did I pass one for the second one? Did I pass one for the third one? How did I do it? So if you want to have default parameters, you need to start from right to left. And if, for example, this is a different parameter, if you're choosing names for that, or if you have a certain order, and you definitely want to have this as a default value, you should just replace it and put it in the end here if it's a different data type or a certain specific parameter that you want to have a default value for. But this is how you define default values in C++ for functions. All right, so last but not least, we're going to talk about something that's going to be very interesting for those who are actually interested in what's happening behind the scenes and are actually interested in some of the memory management involved in C++. Because we talked about storage classes already, and we mentioned the storage class static. And we said that if a variable is defined static, it means that essentially when you enter the scope where this variable is defined or this value is defined, you're allocating memory and you're not freeing that memory until the program is terminated. So let's say we have a function, I don't know, let's just have it a void function, my function, and this function has a certain scope. Inside of that function, we have certain things that are only visible inside that function. Of course, if I define an integer x here equals 10, I'm not able to access that integer in the main function. So it's only valid inside of that scope. And what C++ usually does, or what the compiler usually does, or what we do at runtime, is we enter that function code. So for example, if I call it in the main function here, I call this function, I enter the function code, I allocate memory for x, and then I do something with x. I don't know, I print it, I calculate something with it, whatever. And then we get out of the function either with the return statement or just because we reached the end of the function. And then we go back here, we free the memory for x, and next time, you know, we can do something here, and next time I enter my function, again, we allocate x again, we do something with x again, we free x again. And we said that by specifying the keyword static here, we don't do all of that. We allocate once, so the first time I enter my function, we allocate x, or we allocate the memory for x, and then we don't free that memory until we terminate the program. So why is that even important? What does that even mean? What are the effects of this? And we're going to show, or I'm going to show to you what the effects are. Let's say we're not using static here, and all we're doing is we are having a value x that we initialize at 0, let's say, and then what we do is we just say x plus plus, so we increase x by 1, and then we just print the value of x. Let's say that's all the function does. It creates a variable, sets it to 0, increases it by 1, and prints x. Now, obviously, all this function is ever going to do is it's going to print 1. All the time it's going to print 1 over and over again, no matter how many times we call that function, because what it's doing is it's creating 0, increasing it by 1, and then printing that value. It's not too complicated. Now, this changes when we just add the keyword static here. And it changes because x is not freed anymore. So if I go ahead and say run here, you're going to see that we get 1, 2, 3, 4, 5, 6. This is because the first time we initialize x as 0, but then we cannot initialize it again. It already exists, the memory is not freed, it's already allocated. So this line of code here is not even important anymore because we see it's static, it's already there, so we don't have to allocate it again. We can just use it. So next time we increase it by 1, we increase it by 1 all the time, but the value is never reset to 0 because we don't initialize this this variable again. We don't have to allocate the memory again. We don't have to go through the initialization process anymore because this value is static once, or this variable is static once it's allocated. It stays allocated until it's freed manually or by terminating the program. So in this case, we get a result 1, 2, 3, 4, 5, 6. So this episode today is once again going to be a little bit more technical. We're not going to talk about surface level stuff here. We're not going to talk about basic programming structures like loops or conditions or functions. We're talking about what's happening actually in the memory here, or what's happening actually on a lower level when we do a call by reference and a call by value. So let's say, for example, we just have a basic function here called myFunction, and this function accepts an integer as a parameter. And what it does with that integer is it increases it by 1, it increments it, and then we just go ahead and see out the value like that. There you go. So a very simple thing. And now what we do in the main function here is we say int a equals 10, and then we call the my function on a. So what happens here is a so-called call by value. What happens here is we take a, assign 10 to it. Now the variable a has the value 10. When we call my function and we pass a as a parameter, what happens is that this integer here, this integer x, takes on the value of a, then x is increased by 1, and then x is printed. This does not mean that we're actually passing a to the function. And we can see that this is the case because if after the function I go ahead and see out a, we're going to see, when I run this, that a is not going to be changed. You can see we assign a to be 10. We call the function on a, which then prints x, which is 11, because we take 10 as a value, increase it by 1, see out it onto the screen. We get 11 as a result. But then we again see out a, and we can see that a is unchanged. Because when we pass a to my function, we're not passing a itself. We're not passing the variable a, the object, the memory address a, to the function. So when we call x++, we're not actually calling the plus plus on A, we're calling the plus plus on X, which has the value which was given the value of A. So because of that, A is not changed. Now, this is different from the call by reference. The call by reference, if we want to do one, we need to specify here that we don't pass just X, we pass the address of X. So what we do here is we pass a reference to X, or actually not to X, but when we pass something to my function, it is not just the value, but we take the actual address of that thing. We take the actual reference to that thing. So in this case, what we do is we don't just copy the value of A into X, but we copy A into X. A is X, or X is just a reference to A right now. So if we go ahead and run it like that, you're going to see that the output is different because now we're passing the actual thing. I hope that's not too confusing here. So by using that operator here, and we're going to talk about this operator when we get to pointers, this is a little bit later on in the series, but this operator here refers to the memory address of this variable. So when we pass A, we're not just passing the value 10, we're passing the actual address of A, or it's interpreted as the actual address of A. And then when we call plus plus, we're actually calling it on the A variable and not just on a variable that was initialized with the value that A had. So this was the basic difference between a function call by value and a function call by reference. And now what we're going to do is we're going to look at something called aliases, which uses the same principle that we just discussed to create aliases for variables. So let's say we have an integer I1, which is 10. And now I want to create a second variable that is just the same thing with a different name. And for this, I can go ahead and say int, and then the same symbol here, the and. For example, integer 1, or you can call it ABC123, whatever you want, as long as it's a valid variable name. So what we do with that is we just assign I1 to it. And this is all we need to do. And right now we have two exact same objects, integer 1 and I1. It's the same thing. And we can use both as an alias. So this is nothing but a simple alias, just another name for the same variable, for the same object, so to say. And we can see that this is the case by printing out, first of all, we can of course print out integer 1. But then we can do also something else. So let's first run this. And you're going to see we get value 10 here. But we can also go ahead, for example, and say integer 1 plus equals 90, for example, and then we can go ahead and print not integer 1 but I1, and you will see that the changes that I applied on integer 1 are now also applied on I1 because it's the exact same thing. Click the wrong button, sorry. Oh, there you go. We got 100 even though I'm printing I1 and not integer 1 in the end. So by specifying an alias like that, I just choose another name for the exact same thing. I'm just creating a second variable with a certain name that is the exact same reference as I1. So we can use this to create aliases here. Alright, so the basic idea behind a header file is that we can include functionality from other source files. And imagine you have a big program, a big C++ application, and it has tons of functionalities, tons of functions, constants, all of that. You usually don't want to put all of this into one file. You don't want to have 1,000 functions down here. You don't want to have 1,000 constants up here and so on. You want to usually split that up into different files. And what you do in C++ to do that is you create a separate source file with the functionality, and then you create a header file that allows you to just include that source file. So how can you think about that? Let's say we're going to create a new folder here. We're going to call it includes. This is not mandatory. I just like to do it like that. I also think that it's a better practice to have a separate folder or directory with your includes than to just have them all in the same directory. And what you do here is, let's say we have a certain module that we call calculations.cpp. And in here, we're not going to have a main function. We're just going to have some functionality, so some functions essentially. And we're going to do some very basic functions like int add, int x, int y, return x plus y, int sub, int x, int y, returns x minus y. And we can also have a basic, I don't know, void output message. And we're going to give it a string. So for this, we need IOStream in here. I'm going to give it a string, std string message, and we're just going to output that message. So we're going to say std cout message std endline. There you go, like that. So those are the functions that we now have defined in this calculation CPP, whatever. Usually, of course, you will have different source files for different more complex functionalities. For example, if you have a video chat app, you could have one CPP file for the video recording or for the video processing itself. Then you could have an additional source file for the actual sending of the video data via sockets with all the packaging into structs and into bytes and so on. So you have just different functionalities outsourced into different files. And in this case, we want to include this file into the main CPP file. And theoretically, what we could do is we could just go ahead and say include. And the convention is that when you include your own libraries, you're using quotation marks. When you include libraries of the C++ library, so commonly used libraries, you're going to use these angle brackets here. In our case, so we're going to use these quotation marks, and we're going to say includes calculations.cpp. So this would be possible, but it's a bad practice, as I like to always say. So we can see that this is possible by just saying std cout add, and you can see we already find that function, even though it's not defined in this particular file. I'm not sure if it's going to find it if I remove the include statement. No, then it's not going to find it, as you can see. So VS Code is quite intelligent here. Calculations dot, or actually, sorry, includes calculations.cpp again. We can now use the add function here and just add 10 to 20, for example, and then print the result, as you can see. So we're going to just run this, and there will be no problem with that. Now this, however, as I mentioned, is a bad practice because for many reasons. First of all, it's not the convention. Second of all, sometimes you will want to keep the CPP file, the actual implementations of your programs, you want to keep them private. Not always. Sometimes you're going to do open source. Sometimes it just doesn't matter. But sometimes you don't want to give the CPP file to people. You just want to give them a file that tells the user, or the actual user of the library, what functionality does this CPP file have. So what are the function signatures? What can I do with them? And then when you include it, you just work with it without being able to look at the implementations. And for this, we use header files. So what we do is we create a second file that we name exactly like the source file. So calculations, it has to have the same name, .h. We're not going to call it CPP, but .h. And in here, what we're going to do is we're going to put all of these definitions, but without the implementation. So we're going to say very simply int add int. That's it. Int sub int. And we're going to need IOStream here because otherwise it won't recognize the string. At least I think that's the case. Void output message std string is the parameter. So as you can see, we don't have any functionality in here. We also don't really say that we're including anything. Just because it has the same name, it's going to be linked later on to the source file. And now what we do is here we don't include the CPP file, we include the header file. And because we're doing that, we're actually accessing the functionality of the CPP file. So as you can see, this file is only related to the headers files, only including the header file. This header file in here only has the signatures. It's not implementing anything. It's not even including the implementations from CPP. It's just linked because it has the same name. And then because of that, we can still use the add function in here. But in order to be able to do that, we need to compile and link it in a right way. Now, if you just go ahead and click F6 using the VS Code compilation plugin for C++, you're going to see that this is going to fail because you're actually just compiling main.cpp without any connection to the includes here. Even though it's written inside of this here, by just specifying G++ main.cpp, we cannot really compile that. So if we want to link all these files, what we're going to do is we're going to open up a new terminal here, and we're going to say, first of all, I'm going to show you that it doesn't work that simply. You cannot just type G++ -o main exe and then just go with main.cpp, because then, of course, you get the exact error that we got before, because what is add int int? We don't know that. If you want to know this, you also need to compile the other source file. So we also need to say calculations, actually includes calculations.cpp. And what you're going to end up with is a main.exe file that is one single file, but still has the functionality that we want it to have. So as you can see, we get 30 as a result when we run it, even though we actually are not implementing the add function in that file. So obviously it recognized that calculations CPP is actually where these functions are implemented, and since main CPP is including the source file, it is able to do that. So you can also see as a proof that this is the reason why it works, that if we remove this here, first of all, of course, we're going to get an error in Visual Studio Code, but we're also not going to be able to execute this command here. So it's still not declared in that scope. So we need to have that include statement. We need to have that header file. We can also try to remove the header file, of course, but then obviously it's not going to work because this is a reference to the header file. So you can see that this is how you need to do it. You need to have a header file with the signatures. Then you need to include that header file, and then you need to have another file with the same name, a source file where you have the implementations. And the reason you use a header file is, first of all, for structure. You don't want to have any implementations in the header file, but you also use it because it's just a way to hide your source code, or to keep it away from the end user, so to say. End user, in a relative sense, because you're still a programmer, but that's the basic idea behind using header files. All right, so global variables are actually a very simple thing. The only thing that you need to know about them is that they're accessible everywhere. So we already talked a little bit about scope when we have a function down here. Let's call it int my function. And it does something, I don't know, it returns 0. And we have some variable in here, int x equals 10. Whatever we want to do with that variable, we can do it in here, but we cannot do it in here. So x is not something that we can find here. This is not only because that function is defined down here. It's also the case if the function is defined up here. So we cannot really access x because it does not exist in main. The same way, we can also not access any variables that are inside of main and not inside of my function. So I cannot just go ahead and say int a equals 100. I cannot access a in here, so I cannot say cout a or something. This is just not possible because it's not in the scope. So whatever I do, what I define in here is going to be valid and accessible in that scope. What we define in here is going to be accessible in that scope. But we can also define something up here, global variables. So we can say int x equals 100, for example. We're going to delete this here, and we're going to delete this here. And we can actually go ahead right now and call or access that variable in this myFunction function. So we can go ahead and say std cout x std endline, and we can call my function here. I mean, we could call it if we define it, or we just put it before main. So when we run this here, you're going to see that we can access 100. So this variable up here is accessible everywhere. It's accessible throughout the whole file here, but it's also accessible from other files. And we're going to see what that means in a second. But we can also change it. This is something I want to show to you. We can also go ahead and main and say plus equals 10, and then we're not going to get 100 as a result, but 110. As you can see, 110. So this is clearly accessible throughout the whole file. So in all these different functions, if I open up an if block here or a while loop, it's also going to be accessible inside of that. It's global, so to say. Now, we're going to create a directory here, which we're going to call includes. And in here, we're going to create a header file and a source file. We're just going to say my file.cpp. And then we're going to have, my file.h. We talked about header files in the last video. And let's say we have just a very basic function here, which we're going to call, I don't know, int add to x or something. And we're going to pass an integer here, integer a, or let's call it I, integer I. And what we're going to do is we're just going to return x plus I. Now, what is x? Of course, we don't know what x is, even though it's globally accessible. We cannot just type x and it's going to be recognized here. And of course, we're going to, in the header file, we're going to specify the function signature. So we're going to have an integer add int like that. And here we're going to include the header file. Actually, like that. There you go. We're including the header file, but now still we don't know what that x is. How can I access this x? It's visible, it's possible, but how do we actually specify that? And actually we have already learned that in a storage class video, but we didn't really understand what header files are back then. So we're going to recall that knowledge. It's done by using the extern storage class, the extern keyword. And I think it should be enough to do it here. So we could actually say extern int x, but I'm not sure if this is really the case, if it's really that simple, because I don't think that the source file will be... No, I think we actually need to do it in the C++ file here. So we need to say extern int x in here. If I'm not mistaken, we're not going to do it here. So right now what happens here is we say extern int means that there is this variable int x somewhere. We know it's there, we know it's outside of this class, and we know it's already defined. We don't need to define it, we don't need to initialize it or something. We know it's there and we're just going to use it. So if you know it's there, using the extern keyword to say it's defined somewhere else. In this case, it's defined in CPP. And of course, if we have a bunch of different pairs of CPP file and header files, so just a bunch of different source files and header files, we can use X there as well, because it's accessible, it's global in this file, and it can be used in this file and in any other file that will be linked later on. So let's just go ahead and see if that works. I think that's actually it. We just need to call the function to see it works. So we're going to say not X, but we're going to say add to X. Actually, we need to call this add to X, sorry. There you go. Add to X 10, for example. And we're not going to do this here. There you go. Of course, this will not work because I pressed F6. We learned in the last video how to compile this properly. So we're going to say g++ -o main.exe, and then we're going to say main.cpp and or actually includes my file.cpp. And when we have done that, we can call main.exe, and you can see we get 110 as a result, because what we do is we call add to x, we pass 10 as a parameter. Here we say x is defined somewhere else, so we're going to find it, and then we get that x that is defined somewhere else and add it or add 10 to it and then return that value. So as you can see, it worked. We can also, of course, do it the other way around. We can also specify one here. We can say int test equals, I don't know, 20, and here I can say extern int test, and I can just go ahead and print it, right? So I can just go ahead and say cout test, and we're going to be able to do that because in the same way, this is a global variable. Now, there's one thing that we can do if we want to have this variable global, but only in this file. So if we want to have a global variable x, let's say here, but we don't want this variable to be as global as it is right now. So we don't want to be able to do this here. We don't want to be able to have it being used in other source files, but we still want to have it defined for the whole file here. So we want to use it in here and everywhere else. we can just go ahead and call this a static int. So we're going to say static int x equals 100, and then we can no longer use it in other files. So I'm not even sure if this will compile, to be honest. Okay, I need to type it again, g++ -o main exe main.cpp and myfile.cpp. And you can see, no, this is not the mistake I was waiting for, includes, there you go. And as you can see right now that there's an undefined reference to x because it is static. If I remove the static, you will see that this is possible. So we can compile it successfully. If we say this is static, it's going to be still global in this file, but not accessible from other files. Now, arrays are essentially just collections of elements of the same data type. For example, we can go ahead and say I want an integer array, so I specify int and then my array or any other name followed by square brackets, and inside of those square brackets we can say how many slots do we want to have in that array. So let's say we allocate 20 slots, for example, which means that we have an array with 20 spaces for 20 integers, so a space for each of those 20 integers. And if an integer takes up 4 bytes in this case, we would have 20 times 4 bytes allocated, which means that we have a section in the memory, in the RAM, in the stack, so to say, where we have the array placed inside there. And we can write values and read values from there, but compared to other languages like Java, for example, we can not only do that, we can also go beyond the limits, which is not recommended. We're going to talk about what happens there. But this is something that you can do in C++. You can go beyond the limit. So if you allocate 20 slots, you can also go to 35, for example. But the problem is, of course, is we don't know what happens then. And we're going to talk about that in a second. But for now, let's look at how we can actually access the individual values here. So let's say we want to print a certain slot. What we do is we say cout my array and then the respective slot, for example, 7. Now, what you need to know if you have never worked with arrays is that arrays start, or the index of an array starts counting at 0 and goes up until the size -1. So the first index here would be index 0, and the last one would be index 19 if you want to stay in the boundaries. And now the problem here is, or it's actually not a problem, but the interesting thing here is that we're printing something that we haven't assigned yet. And we just have this array, we've allocated the space, but we haven't set what should be inside of that space. So what we did here, or what the compiler or the system does here, is it says, okay, this range here of memory, this section here is for this array, but we don't do anything. So this section may have already some values in there. It can have values from previous stuff, it can have some random values, it can have zeros, doesn't matter. We just allocate it, we don't change it, so the values that are in there are still in there. So we can go ahead and see what we get here in this case. It's totally random and undefined, we cannot really know. In this case we get a 0, so let's go ahead with a for loop and print all the values int I equals 0, I less than 20, I plus plus. And we're going to print all of them. And in this case, you can see we have a bunch of random values here. These are all the values that were already inside of that section that we allocated for the array. If we don't want to have all these values still in there, we can also overwrite them with zeros by just saying equals and then 2 empty curly brackets. If we do that and run this again, you will see that it's full of zeros. Down here, as you can see. So this is one thing that you can do if you care about what's in there in the first place. We can also go ahead and overwrite the first couple of slots manually. So we can say, for example, I want 10 in there, I want 80 in there, and I want 20 in there, and the rest shall be 0. So we can do it like that. And you will see that the first 3 slots now have these values, and then we have only zeros. So this is how we can create arrays and access the individual fields. So now let's talk about what happens if we go beyond the limit. Now, first of all, let me show you that it actually works. So we can go ahead and say cout my array 50, even though we have only allocated 20 slots. This works in C++. It would not work in Java, for example. I'm not sure if it works in Python. I think Python has some... I think actually it doesn't even work in Python. But in C++ it works. And you can see that we get some value. And this is completely undefined. We're somewhere in the memory that does not belong to this array. We can still access it, but what happens when we do it is undefined. It depends on the compiler and the system. Now, most compilers, what they do is when you, for example, access 20 or 21, it just goes to the next neighboring spaces in memory. But this does not have to be the case. We can end up anywhere and read any values. And of course, the dangerous thing here is that you're not just reading the stuff, you can also write the stuff. So you can say my array 50, for example, equals 200. Now, this works, but what happens, we don't know. Now, in this case, it just terminates, which is even more dangerous than if it crashes. Because you can think about this like that. You have the random access memory. You have the memory where you have all your variables and important values and also jump back addresses. So when you call a function, for example, and this function has to jump back. So let's say I have some function defined and I call this function here. What I do is I jump to that function and then I execute the code in the function, and when I reach the end of the function, I need to know where to jump back. I need to know that I need to come back here and continue with the rest of the code, which is down here. And the problem is that we have all of this basically stored in the stack, which means that if I overwrite if I go beyond the limits of the buffer of the array that I have, I can also overwrite the jump back address. And this can happen by accident, which is dangerous because you don't know what you're overwriting, right? I might have a different variable here, which is very important. Int a equals, I don't know, some value here, 10 for example. I can overwrite that value by writing on this slot, which does not belong to the array anymore. I can overwrite the jump back address. In the best case, my program crashes and I see that I have done some nonsense, because that's really the best case scenario. The program crashes and some error happens and this is it. But the worst case scenario, or something that's a little bit worse than that, is if it continues to run and you don't know what you have done right now, because, you know, why are you changing this value? What does that even mean? This is some value that's there and you're just changing it. And this is not a good idea, and you should never be doing that. And this is also one thing that people do, that hackers do. It's called buffer overflow. Now, it's a little bit more complex than that, but the basic idea is that if you have some input, for example, you have, I don't know, some, I don't know if it works with strings. It should work with C strings. But you have some user input here where you say C in S. And what you do then is you can string copy this into a string buffer, which, or into a character buffer actually. So you have a certain amount of characters that you can store. Let's say you have a buffer and character array like that, character array of size 50, for example, and then you take some user input that has a different size. It's a dynamic size, and the user passes something that has 100 characters. What happens is you fill up those 50 characters, and then you go beyond that and write what the user has put into the program. Now, this is dangerous because the user can put instructions in there that overwrite the jump back address and then execute the code inside of that buffer here, which can lead to all sorts of different hacker attacks. It's called buffer overflow. You can Google it. It's a very dangerous thing, so you should never go beyond the limits of what you have allocated. Now, one last thing that I want to show you is that you can also define the size of the array by using a variable. So let's say we have this int a here, and we're going to see in the value of a, and then we're going to allocate a slots, and we can see that if I go from 0 to a plus 10, just to see that after that it's no longer allocated, we're going to print all the values here. So we're going to say std, oh, forgot the std here, std cout my array I std end line. And you're going to see that we're now going to have those three values here, then a bunch of allocated values of size A, and then we have 10 values that we're going to print that are not allocated. So just that you can see that we have a dynamic size here. So let's choose 60, for example. As you can see, we have 60 zeros, or actually 57 zeros, or yeah, 57 zeros, or actually, why is it 60 in the first place here? Oh, 60 is my input, sorry. And then we have a bunch of unallocated values, the last 10 here. So you can see that we can use this to create a dynamically sized array. However, I don't think that this is supported in all C++ versions, or in C even. So sometimes this is not really possible. Sometimes I'm not sure what it depends on, compiler or version or standard. But sometimes this does not work unless the integer is a constant integer. And sometimes you just need to pass static values. And if you want to have dynamically sized values, you need to use a function called malloc that we're maybe going to talk about in a future video. But in the version I'm using here, and maybe in the version you're using at home, we can do it like that. We can just create an integer, assign a value, and then use this as the size of the array. So we already talked about strings when we talked about data types, and we said that they are the text data type. And in today's video, we're going to talk a little bit about the different functions, about the different things that we can do with strings. And we're also going to talk a little bit about the history of strings. We're going to compare C strings to C++ strings. Because the important thing here is that even though we're coding in C++, we can still use C code and we can still use C libraries, because sometimes we're going to encounter modules or libraries that we want to use, or we have to use, that are written in C. And in C, there is no string class. So in C++, what we can do is we can just say std string my text, and we can say this is now my text, and I can assign hello to it, and I can work with it. And this string thing here, this my text, is a string object. This is an object, an instance of a class string. Whereas in C, we didn't have any classes, we didn't have any objects, we only had primitive data types, structs, and so on. So we had to come up with a different way of storing strings. And strings in C were just arrays of characters. So the basic thing that you do in C in order to create a string is you say character, and then you say, for example, text and an array. So you make a character array. This says it's an array. We talked about arrays already, and we can say now, okay, this array has 10 positions. And we can say this is just hello, like that. And the important thing is here, on a lower level, we can say that actually, even if we say 10, we are actually allocating one more, because we also need to have the \0, I think it is, the null terminator that says, okay, this word is now over. And those are now the C strings. So essentially what we can do with them is, of course, we can print them out. We can say cout text is just a character array that's initialized like that. And then we can say std end line. And we can go ahead and run this. And you're going to see that we get hello as a result here. Good. So this is one way to do that. You can also say character, or actually let's say character text 10. And then we can say text 0 equals h. I mean, actually, we need to use single quotations here, h. And then we can say this one here is e. And then the third one we could say is y. So we have the word hey. We can do it as like that as well. So we just have to compile this here. And you can see that we have hey, but we also have the other characters here as well printed out, because we have 10 slots. We can also say we want to have 3 slots, and then we can just create this simple C string here. What did happen here? Oh, I think we didn't add a null terminator, so it doesn't know where to stop. I'm not sure if that's the problem, but we could actually say 4, and we can say text 3 equals, I think it's \0, if I'm not mistaken. Let's see if that's true. And we get, yeah, I forgot the semicolon. But now we get hey as a result. And if I run this again, we should also get hey as a result, yes. So it's important that you also specify the null terminator if you do it manually. If you do it like that, if you do a direct assignment, I think you don't need to do it, or actually we can say 3. I think you don't need to do it manually, because by nature what happens here, it's too long. Oh yeah, okay, we need to allocate 4, in order to store 3, because then it can add a null terminator in the end. That's the idea. So essentially, in a nutshell, you create a C string, which is an array of characters, and you always have to allocate one more than you want to write into it, because then you have, if you do it like that, if you initialize it with that assignment operator here, if you do it like that, you need to take into account that you have to add a \0 then in the end, or that it does that for you automatically. If you assign the individual positions by yourself or on your own, you need to add it on your own as well. So now let's go ahead and take a look at what we can do with those C strings. Now, first of all, we can go ahead and just print their size by saying size of text. Now, the important thing is that here you don't get the amount of characters in terms of, the word. So in this case, you won't get 3, you're going to get 4, because the size of the text is 4. Even though we have the null terminating symbol here that we don't see, it's still going to be 4, because the size of the array is 4 in this case. And remember, size of gives you the amount of character memory units, which means that if a character, like in most systems, is 1 byte, you're going to get the amount of bytes. But if a character for some reason is 8 bytes and you get a size of 2, this means you have 16 bytes of size. This is just a minor detail here. But essentially, the important thing is you get the size of text when you're using the size of function, of course. If you want to have the string length, which is the length of the amount of characters that we have in here, the amount of letters, we have to include the string module here. So we have to say include string.h. And then we have to go ahead, and instead of size of, we're going to use string length. So strlen. You can go ahead and run this here. You can see 3 is the result, because we have H, E, and Y. We don't have the null terminating the \0 symbol here. We don't have it. Yeah, we don't take it into account. Of course, we have it. And now we're going to introduce some more functions here, and we're going to get a little bit into cybersecurity, even though this video is called strings. We're going to talk a little bit about hacking. Now, obviously, we're not going to really talk about hacking in terms of, how to do something, but we're going to mention some cybersecurity aspects of these functions, because as I already said, nowadays we use the string class. We don't use C strings, and one reason for that is because the functions that we have to use with C strings are very insecure and have a lot of vulnerabilities, or are dangerous if you don't know what you're doing with them. And for this, we're going to introduce the string copy function. Now, this function is very dangerous if you don't know what you're doing. Why is it dangerous? Because let's say we have some array here. So let's say we have character, text, and we have, 16 bytes for this one. Now, what happens when we call the string copy function? The string copy function essentially takes one string and copies it into another string, into a C string. So what we do is we specify one character array, in this case text, for example. This is the destination, and then we also specify what we actually want to save into that text array in this case. Now, actually, let me delete that, because I now notice that I have used text 2 times. So this could be anything, right? We can also go ahead and say, actually, I'm not sure how we would do that. But let's say we have, let's say we get some input here, like character text 200, or actually we can do text 200. Actually, we can do also a malloc, but we haven't talked about this yet. Imagine you have some dynamic user input. In this case, we're just going to say 200, even though it could be dynamic, it could be everything. Let's say we have some input here. So let's say we have this buffer of 200 bytes, and then we allow the user to enter something into those 200 bytes here. And what we enter into those 200 bytes here is going to be stored into the first text array. Now, you're going to see what the problem is probably here. The problem is that we're getting an input of up to 200 characters. And the problem is that what we're doing here is we're just getting any input and we're saving it without checking how long the input was or anything. We're saving it, we're pushing it into a 16 bytes array. Now, what this does is not giving you it's not going to give you a error message here. It's not going to tell you, oh, this doesn't work because we're out of bounds. It's just going to go over it. It's just going to go over the boundaries. We've talked about that already. So imagine you have, I'm going to do this with smaller numbers now. Let's say you have 4 allocated slots for your string array, and now you save something that has 8 bytes into it. Now, what happens then is you allocate this, not allocate, you write into this, you write into this, you write into this, you write into this. And what happens then is you write into the next one, and the next one, and the next one. Now, first of all, it's undefined where you're actually going to end up writing, but the point is you're going to write outside of your array. And this means that you can also overwrite jump back addresses of functions, you can overwrite other variables, and this is something that is exploitable in so-called buffer overflow attacks. So the idea is, in this case, this is very low-level stuff. You actually need to understand assembly most of the time and not just C. You need to understand what's happening on a very, very low level here. But the basic idea is, first of all, I have, oh yeah, of course, stdcin, sorry. The basic idea is that I have the possibility right now to just input some text. And of course, I can go ahead and input hello, which doesn't cause any problems. But of course, I can also input something that's way more than 16 characters long. So let's say I input a. Now, this is way more than 16 characters. In this case, you know, I don't know what happened, right? I could have overwritten a jump back address. I could have just changed the value of something. I could have accessed some memory that I'm not allowed to access. I don't know what's happening here. And the compiler doesn't know either. So it's determined during runtime what actually happens here. But the point is that if I run some software like GDB and I get the memory addresses, I get the structure of the program, I look into it and I check, okay, how does this work? Where are the individual jump back addresses? Where do I need to go? I can inject bytecode into this here. So I can go ahead and figure out, okay, where is this variable? Can I somehow get into it? Can I somehow navigate the jump back address into that array? Can I somehow inject bytecode that allows me to have some malicious piece of code in that buffer and execute it? And it sounds very hacky and geeky and so on, but it's actually how buffer overflow attacks work. You just need a function like that doesn't check for the length, and now you have something that's way longer than 16 bytes and allows you to go beyond the borders, and you can just overwrite different parts of the memory, not just the text buffer, not just the character array that you are supposed to write into. Using that string copy function, you can just write beyond the borders. So this is a very dangerous thing, and you need to take into account that this can go wrong. All right, so after that long talk about security issues with string copy, let's also talk about string compare and string cat. What these two functions do is a very simple thing. String compare compares two strings. So we have text and text2. And this function is going to return 0 if those two texts are the same, and I think less than 0. I mean, we can actually look into the man pages here. Man string compare. Let me just see. It should return less than 0. Yeah, there you go. Returns less than, equal to, or greater than 0 if S1 is less than, match, or greater than S2. Now, of course, you have to define what less than actually means. So what is one string being less than another one? Probably the length, probably the characters in alphabetic order. But essentially, if this text is less, mathematically less than text2, this would result in a value below 0, otherwise above 0. And if it's the same, if they match, if they're the exact same string or text, we're going to get 0 here. And then we have string cat, which stands for concatenate. What we do here is we essentially just say one text and another text, and then we concatenate them. Again, I'm not sure if we're going to get this as a return value. So let's say man and string cat. And here we get, we get the character pointer as a return value. So this means that we're going to get the string, the concatenated string here. So we could say character concatenated, 200 equals string cat of text2. Now this, of course, is again dangerous. We should probably say 216. But this is how you can concatenate strings when you're working with C strings here. All right, so now that we talked about the outdated C strings that you're going to still probably encounter as a C++ programmer, let's get to the more modern strings, which are a string class or string object. So here we just say std string, and we say s, for example. Now, one thing that you need to know here right ahead is that if you just write string s, this already creates a new object in the memory. Now, in Java, this is not the case. So in Java, you would have something like class name, whatever, and then name, then new class name. This is how you do it in Java. This is not how you do it in C++. You don't need to do that in C++ by just saying string s or any class name s. You just create a new instance right away. You don't need to do anything else. Now, however, you can go ahead and directly assign a value as well, like that. Or you can go ahead and do it like that. std string s2, and then in the parentheses, hello friends, like that. And we can go ahead now and see out the result to see what we have in those objects. Come on, there you go. And you're going to see hello and hello friends. Good. So now let's take a look at all the things that we did with C strings. How do you do them with string objects? Now, first of all, we got the length. We had the string length function for the C strings. Actually, let's just find out if we can still use it, because I'm not even sure if that's possible. String length of S, I don't think actually it's going to work, but maybe it will surprise me. End line, sorry. No, it doesn't work. Or does it? No, it doesn't work, because you need to have a character array, a character pointer. So what we do here in order to find out the string length of a C++ string is we just go ahead and say s, or string name, dot length, and this is a function, or actually, technically speaking, it's a method that we call onto this object. So this object here, string, is not, or s, is not just a string, it's not just a text value, it also has different functions and attributes. And one of them is the length function, and when we call the length function, we get the amount of characters in that string. Again, without the null terminator, at least I think. So let's see, 1, 2, 3. If it gives me 3, it's without the null terminator. Yeah, and if it would give me 4, it would be with the null terminator. So this is how you get the length of C++ strings. Then we also have, one thing that you should also mention here is that we can still index the individual positions. So I can still go ahead and say s at position 5, like that. So this still works. Does it work? Oh, maybe I got the white space. Lucky me. Yeah, there you go. I got the white space. But a technically cleaner way to do it would be to say std cout and then s.at6. This would give me the same result here, but it's considered to be more best practice, better practice if you want. So if you can, use this one and not this one here. So this is how you index the individual characters. And now we also have the functions called compare and concatenate. And for this, we don't even need functions with C++ strings. We can just go ahead and compare them by comparing them. So we can say if s equals s2, then do something like cout same or something like that. And otherwise, std cout not same. So in this case, we should get a not same because they're not the same. Surprise. And if we change them later on to the same, so first of all, we get not same, and then if I say hello world here as well, we should get same. And we do, as you can see. So in C++ strings, we don't need to call functions like string length, string copy, or something. We just go ahead and we compare them using the comparison operators. Of course, this also works with less than and greater than, less or equal to, and so on. And for the, what was the last one we had? The concatenation. What we do for that is we just use the addition, the addition operator. So what we do here is we say std string combined equals, for example, s plus s2. I think this should work. Let's see if it works. Combined. Surprise me. No, it works. As you can see, this is how you concatenate strings with C++ strings. So let's talk about the basic idea behind exception handling. Now let's say you have some piece of code here And this piece of code is prone to errors. You can get some errors or exceptions here. Something can happen that you don't want to happen, but you cannot necessarily say, okay, you cannot prevent it with ifs, because whenever you can prevent something with ifs, you want to prevent it with ifs. But sometimes things happen during runtime that you cannot prevent with ifs, or it's hard to prevent them with ifs, or you don't want to do it. So in those cases, what you want to do is you just want to run the code, and in case something goes wrong, you want to do something. Now in Python, for those of you who come from a Python background, we have the try except structure. So we have a block where we try something, and then in case it goes wrong, we execute the except block. For those of you who come from a C background and you don't know any other programming languages, which I don't think that anyone out there knows C and no other language, but nevertheless, if you come from a C background, you know that there are error codes. You don't know what try catch is, and you don't deal with exceptions, because in C what we do is we have some piece of code, for example, I don't know, printing something, whatever, and or actually printing something is probably the dumbest example that I could have come up with, but let's say we have something like opening a semaphore or closing a semaphore. Whatever happens, it can return an error code. So let's say we try something, STH for something, and if this something returns the error code -1, we go in here and we do fprintf. You don't need to learn this, this is just C, and you have some error message that you send to std error and so on, blah blah blah, whatever, and then you go exit failure, like that. That is the C way of doing things. In C++, we don't do it like that. We can still do it like that, but you don't have to do it like that, because in C++ we throw exceptions and we catch those exceptions. So imagine we have a function up here called divide. It takes two floats, float1 and float2. And the basic idea here is if f2 equals 0, because division by 0 is undefined. Now C++ lets you do that. Let me just show you that it does. If I go ahead and say cout 10 divided by 0, this will not give me any errors. What happened here? Doesn't give me errors, but it doesn't give me an output either. I think if we do it like that, float f1, float f2, cin f1, cin f2, and then we do f1 divided by f2. And I now input 7 and 0, we get infinite or infinity as a result, which mathematically speaking is not correct because the division by 0 is undefined. So this should not be infinity necessarily, unless you define it to be infinity, right? But let's say we want to create a function that does not allow a division by 0. What we could do is we could say, okay, if the second parameter here, if the second number is 0, throw an exception. So we use throw, the keyword throw, and then we can specify an error code here. So let's say we specify 15 for whatever reason. And now what we can do here is we can say, we're not going to use the division here. We're going to use the divide function. We're going to pass f1 and f2. We of course need to say what happens else. Otherwise, we're going to return f1 divided by f2. And if we now run this, I can go ahead and say 7 divided by 4, and we get 1.75. I can say 8 divided by 2, and we get 4. And now I can try to say 9 divided by 0. And you can see terminate called after throwing an instance of int. So we got an exception here. So we can do it that way. We can either write our own functions that throw exceptions, but even if you don't want to do that, there are libraries out there that just throw exceptions when something goes wrong. So for example, when you try to open a file that doesn't exist, when you try to do stuff that you should not be doing, or when stuff happens that should not be happening. And what we can do instead of letting the program just crash, because now, you know, whenever you get an exception, the program crashes. And if you don't want this to happen, you can use a try catch structure. So you say try this piece of code, and if something goes wrong, if we get an exception, catch this exception. And in here, we just have to specify what kind of exception it is, int e in this case. And then we're just going to say cerr, which is like cout. So if you don't use std, you should be writing std cerr. Don't forget that, best practice. And then we say error, for example. Like that. So now if I try to divide by 0, we get error. Now, of course, in this case, the program also terminates, but if we had some code down here, like cout test or something like that, it would still run that piece of code. And we would get this if we wouldn't catch this. So if we remove the try catch structure here, we would not see the last line of code. So if I say 7 divided by 0, it terminates immediately when the exception is thrown. So with try catch, we can catch the exception, which essentially means that we have taken care of it and we can proceed with the rest of the code. Now, if you want to distinguish the individual error codes, you can go ahead and say if e equals 15, for example, we can say cout division by 0 is undefined, and otherwise we can just print a general error message like that. So in this case, if we have something like 6 divided by 0, we would get division 0 is undefined. If we get some kind of other exception here, we could also, or we would still print error, a generic error message. So let's get started with pointers. Now, pointers are a very essential topic when it comes to lower level programming in languages like C, C++, Go, Rust, and so on. And what it basically does, or what a pointer essentially is just something that points to the memory address of another thing. That's maybe not the most scientifically accurate definition here, but it's essentially what it is, right? So we can say we have an integer a equals 10 here, and this integer a has a certain size. We can check that size with size of. In my case, it's going to be 4 bytes. So size of a is going to be 4 bytes here. This means we allocate 4 bytes for this particular integer. Now the question is, where is this integer stored? Now obviously it's stored in the RAM, in the random access memory, but the random access memory has a lot of, you could say, blocks or just slots, you could call them. And those are allocated or not allocated, and of course there are a lot of them that are not allocated. Let's say this represents 1 byte, for example. And we have millions of such of those slots in the random access memory. And what we do when we store an integer is we allocate 4 of those bytes here and say, okay, this is reserved for the integer a. Now, in order to know that we're talking about those 4 bytes here and not those 4 bytes here or something else, we have a memory address. So every single slot has a certain address. And this address is what we can print by using the AND operator. I'm not sure if it's called that, but this operator here. This gives us the address of a, the memory address of a. So if I run this, we're going to get a hexadecimal number here. This is the location where the variable a is stored. Now, if I want to store this location, this memory address in a variable, this is then a pointer. So if I say int, and now I have to use this star operator or symbol, this asterisk symbol. And if I say my pointer, for example, equals end a, this means that this my pointer variable here is pointing to the memory address of a. So I can go ahead, for example, and just print out the value of my pointer like that. And we're going to get the same result. So this pointer has as its value the memory address of a. And we can actually get rid of this here. Now, one thing that we can also do with that pointer is we can dereference it, which means that we can add a star here and say, okay, now I'm not actually asking for the value of the pointer. I'm asking for the value of the thing that the pointer is pointing to. So if I do this, I'm going to get the value of a actually. So let's see if that's the case. As you can see, we get 10 as a result because now, of course, my pointer is pointing to a, but if I'm doing it like that, I'm not getting the address of a, which is the actual value of the pointer, but I'm getting the value behind the memory address. So what is stored there? This is how we can print the value of a pointer. So we can now also go ahead and change the value by using the pointer. So we just have to say star my pointer equals 20. And then we can go ahead and see that A has changed because of that statement here. And the important thing is that you always specify the star symbol here, because that means that we're dereferencing the pointer. We're not changing the actual value of the pointer. We're not letting it point to a different address, because we could also go ahead and say my pointer and then the address of another variable. So we could actually change the value of the pointer as well. But by using the star symbol in the beginning here, we're changing the value of the thing that the pointer is pointing to. So in this case, we would get, oh, wrong thing here. F6, there you go. And as you can see, we get 20 as a result here because we changed the value of A by using the pointer, by dereferencing the pointer, by changing what the pointer is pointing to. And you can see that the actual changes are also applied, or actually only applied to A, and the pointer is just the tool that we use to do that. So now let us talk about pointers to arrays or array pointers. And for this, we're going to first of all create an array with 100 slots here. And what we're doing when we're doing that is we're allocating 100 times 4 bytes in this case, because we're storing an integer and an integer has 4 bytes. So 4 times, actually 100 times 4 bytes. And what this means is that we pick a starting address and then we allocate the next 400 bytes for the values. And in fact, the array itself is the pointer to the first position. So we're going to see that this is the case by just saying cout, and then we're going to print, first of all, the memory address of any index. So we're going to say the memory address of the value stored at index 56, and then std endline. And you're going to see that this is some memory address somewhere inside of this array. And then we can go ahead and copy that, and we can change the values to 0, 1, 2, 3, for example. And what you're going to see is that those memory addresses increase with a step size of 4. So we start at a 0 in the end, then 4, then 8, then C, which is 12 in the hexadecimal system. So you can see we're always progressing or increasing by 4, because 4 bytes is what an integer takes up. So the next integer is going to be found 4 bytes after the starting position of the previous integer, obviously. And now we can also go ahead and print out the address of the actual array, not of a specific index, and you're going to see that this is nothing but just a starting index. So if we do that, we're going to get the same index here, because the index of the memory address of the actual array is the same as the memory address of the first element of this array. So the starting element is actually the beginning of the array, obviously, and the array itself is just this memory address. Or just a pointer to that memory address. So what we could do here is we could just say int pointer equals array. So we don't use the AND array or the AND operator on this array here, because the array in and of itself is pointing to that address. And we can see that this is the case because we can go ahead and say cout pointer. And you're going to see that the pointer is now pointing to the same address as the array. So now let us also talk about pointer arithmetics, which means that we can add values to pointers or subtract them from pointers. Let's say we have int a equals 10, and then we have int pointer is pointing to the address of a. What we're going to do now is we can also go ahead and, after printing the address of a, obviously, we can go ahead and increase the value of the pointer by 1. So we can do this a bunch of times, or actually maybe do this once and then copy that like that. And you're going to see that the address that the pointer is pointing at is changing. So when we run this, you can see we start at this position here. This is the address of A, and then we have again a step size of 4, and we go to the next address and the next address and the next address. And the pointer is now really pointing to a different address. It's no longer pointing to A, which means that if we do something like pointer dereferenced equals 10 or 20, we're no longer changing A. We can see that A is not going to be changed. but we're changing whatever is at this index here. This could be everything. So again, this is dangerous. This is undefined behavior. We don't know what it's doing. We're just changing something. We have no clue what we're working with, because in this context, of course, we allocated just 4 bytes for the integer, then we pointed it, and then we go somewhere else and do some stuff. So this is of course not recommended, but we can also use this to iterate through the individual elements or indices of an array. Of course, you can also just use a for each loop or just a basic for loop, but we can also do this with pointers. We can say int array 10, and then we can say int pointer to the first position is just the array itself, because of course the array is a pointer to the starting position. And then what we're going to do is we're just going to say for int I equals 0, I less than 10, I plus plus, and then what we're going to do is we're going to calculate first position, so the current pointer that points to the first position, plus I, so how many integer steps do I want to go further, and then I dereference that position and I change the value there to, I don't know, I times 20 or something. So if we then go ahead and use a simple for each loop to see the values for x in array, std cout x, you're going to see that the values are actually changed. Now, one thing that you probably noticed is that the step size is 4, and the step size is 4, of course, because we're again dealing with an integer. The type of the pointer and the type of the variable that the pointer is pointing to determines how big the step size is. So again, let's do the printing again here. Let's say again cout. Actually, this is an array. Let's go ahead and say int a equals 10 again. Int pointer equals address of a. Now again, if we start with the pointer and then we just say plus plus pointer, so a pre-decrement increment, sorry. If we now go ahead and do this a couple of times, you're going again to see that the step size is 4 because an integer occupies 4 bytes. And if you say plus, it means go to the next element, and the next element, it assumes it's also an integer. So this means that we're going to go 4 bytes after that all the time, because this is an integer pointer. It points to integers, and those have 4 bytes in this case. If this was a Boolean, if we just say Boolean, and this is true, and this is a Boolean pointer, what's going to happen is we're only going to have a step size of 1 because a Boolean has 1 byte. So you can see B, C, D, E, F, 0, 1, 2, 3, and so on. So this is how the step size is determined. So now let's go ahead and talk about null pointers. Now let's say we have a variable a again, and we have a pointer p again, or ptr again, and this is pointing to a. And now what we want to do is we want to do something with that pointer, do something with pointer, and after that we want to say, okay, this pointer, you're done. You don't need to point at a anymore. And I also don't want you to point to b or any other variable, and I also don't want you to point into a random memory address. I want you to point nowhere. I want you to point absolutely into nothingness. And if you want to do that, you can use outdated ways that I'm going to show to you, because you're going to encounter them as a C++ programmer. And there's also a best practice way which is used in C++. So one way to do that is to just say ptr equals 0 or ptr equals null. Null with capital N-U-L-L. This is the C way of defining null pointers. Now, this works and you can still do that, but it's not best practice and it has some problems. I'm not going to go into too much depth as to what can go wrong here, but the basic idea is that when you're passing it to a function, null is essentially just another way of saying 0, so it's just a name for 0. The value of null is still 0. It's still an integer, a number 0. And this is the problem, that when you pass it to a function, sometimes this function will not know, okay, is this now a 0 or is this a null value? So what shall I do with that? Is this pointing to nowhere, or is this the value 0 that I can do calculations with? And you're going to encounter this null value over and over again if you work with old code or if you work with C code. But in C++, if you have the chance, always define null pointers. So null ptr, like that. This is not an integer, this is not a number, and it's not going to be mistaken as one. So you can use it. This is the best way to say, okay, this pointer is pointing nowhere. The other ones still work, but they have their problems. So use this way if you can. But the good thing about this is that if you say if null pointer equals 0, because old code bases like to do that, because or actually null pointer you're not going to ask directly, but if you say ptr, if ptr equals 0, you're going to get a yes here. So you're going to see this message here because it's going to go into the if branch. Because this is in fact going to be 0, even though it's not the value 0, null pointer is not 0. Null pointer is an actual thing. It's not just a macro as null is. But still it's going to give you 0 when you compare it, or it's going to return true when you compare it to 0, just so it's compatible with older code bases. So now, just for the sake of completeness, I want to show you void pointers. And those are pointers that have the type void, which means that they can point to virtually everything. So we can say is null pointer, we can say is int a if a is an integer. So we can do it like that. We can say int a is this time 20, come on. And then we're going to say std cout vp. So they can point to absolutely everything. They are not limited by a type. However, this is not something that you should necessarily always, use, because this is actually for very, very special niche cases, not recommended for beginners unless you really need void pointers. Sometimes they're necessary, but they can point to everything. And you can also, you can see that this is the case, because if I say something like Boolean, it's not going to work, because we get an error, because this is a Boolean pointer, this is an integer pointer. We cannot do that, but with void it works, because it can point to any type. Now I'm going to still show you one case in which it can be useful. I'm not saying this is a best practice approach to do that, but let's say, for example, we have something like I have a character, and this character is called my character, and it has the value a. And now what I want to do is I want to know the memory address of a. I want to know where is a actually at. And the problem with that is that if I go ahead and say, okay, int my character, we're going to see, first of all, let me remove that, and let me remove that. We're going to see that we don't get the result that we expected. We get some, some string here that is definitely not the memory address of the character. And this is because a character pointer, we talked about this in the string video, a character pointer is interpreted as a string, as a sequence of characters, and not as a memory address. So in this case, we don't get a memory address. We treat this as the starting point of a character array, of a string, of a C string. So if you want to print the actual memory address, you would have to cast this to a void pointer by just saying void pointer, and then you can cast it like that. And you're going to see that you're going to get the memory address of the character. So this is one use case in which it might be useful. I'm not sure if this is best practice or anything, but this is one application of void pointers, for example. Now we have two more things to talk about, and the first one is pointers to pointers. Yes, we can actually use pointers to point to other pointers. Again, I'm not going to go into too much depth on these individual subtopics on pointers, because then I would have to make a 2-hour video, 3-hour video, or something like that. But you can actually say, okay, I have an integer a, which is 10, and then I have an integer pointer ptr, which points to a, and then I have an integer pptr, for example, a pointer, which points to the memory address of the pointer. And this is something that you can do. I'm not going to talk about why this is important or why this should be used. But of course, the pointer in and of itself also has to be stored somewhere. So if we point to the address of the pointer, this is also a legitimate thing. And we're going to see that we get different results. We can actually ignore that. And if I dereference the pointer, I get the pointer. So this is, as you can see, I get the address that ptr is pointing to if I dereference pptr. So last but not least, we're going to talk about function pointers, and they are very interesting because we can go ahead, for example, and define two functions up here. Function 1, which prints out I am function 1. like that. And then we copy this and we create a second function, function2, I am function2. And now what we can do is we can go ahead and define a pointer that points onto a function, and then we can change the value that this pointer has, but we always execute the same function with a different functionality. Now it's very interesting. First of all, we have to specify the return value because, of course, the signature of the pointer is a certain signature, and every function that we point to has to have that signature. So we cannot define a void function pointer and then let it point to an integer function. It doesn't work like that. So we have to say void, then my func, for example, and then after that, the parameter list followed by a semicolon. Now, this is important that those two functions have the same signature because otherwise we cannot just point to them. We have to have both of them return a void and then also both of them have no parameters. We can also say, okay, both of them have an integer, but we cannot say this has an integer, this doesn't have one, or this has an integer and this has a string or something like that. We have to have the same header and the same function signature. And once we have that, we can just go ahead and say my func equals function1, and then we can call the pointer. And you're going to see that we're going to call I am function1, and if I change this to 2, we get I am function2, and we can also change this, and we're going to call the same function, but it's pointing to a different function. I mean, we're going to call the same function pointer, but it's pointing to a different function, and we get a different functionality. So as you can see, we have the same statement, my func, but we call different functions, as you can see. All right, so as the name already says, constants are constant and not variable. So we can go ahead and say const a equals 10, and then we can do everything with that value that we can do with a variable. So we can see out it, we can add it to different values. So we can say a plus 20 and print that. We can also create a variable b and store the value of a in it and then see out the value of b. And we can also, of course, change the value of b. So we can say b equals b plus 50. And then we can see out b again and so on. So we can do all of that. What happened here? A is not declared in the scope. Oh. Const int a, sorry, we need to specify the data type as well. As you can see, this works, so we need to say const. This is just a keyword that says, okay, this is not a variable, this is a constant. And then we specify the data type. If we don't specify const, it's going to be a variable like here. But the one thing that we cannot do with a constant, obviously the name already tells us that, is we cannot change the value. So we cannot say a equals 80 all of a sudden. We cannot change the value because we're going to get the error assignment of read-only variable. This is read-only, we cannot do anything with it except for use it. We cannot change the value of it. We can also not increment it or decrement it or do any other operation because, again, we're getting increment of read-only variable. Doesn't work. We cannot change the value. It's immutable. So this is the basic idea behind a constant. Now, one thing that you should know about constants is that the convention says that the name of a constant should always be uppercase. So in this case, I did it not according to the convention. We have to say uppercase A, or even if it's a word, even if it's my constant, it should be written like that. We should say my constant all in uppercase and not something like my constant or just my constant or something like my underlying constant. The convention says you can either do my constant like that or you can do my constant like that. Doesn't really matter, but it has to be uppercase because that signals, just by convention, not to the compiler or anything, just for the developers, this signals, okay, this is a constant. So this is a convention to keep in mind. Now let us briefly take a look at constant pointers because those are interesting. We can define two types of constant pointers, or we can use the constant keyword in two different ways. So let's say we have, again, the variable a equals 10, and we want to have a pointer to it, and a is a variable, it's not a constant. And what we want to do is we want to say, okay, we have a pointer p that points to the address of a. But now we want to have this pointer to be constant, and we can do this in two ways. First of all, we can say constant int pointer equals the address of a, or we can say int pointer constant p equals the address of A. And let's rename them to pointer1 and pointer2 to see the difference. The difference is between what is constant here. Now, A in and of itself is a variable, so we can always do something like A equals 20, for example. But we cannot necessarily do that by dereferencing the pointers if they have a constant keyword. So in this case, what we're saying in the first pointer here, in the first line, is we're saying the pointer or the object that we're pointing to has to be treated as a constant when we're using that pointer. So if we do something like dereference p1 and assign 20, this will not work because p1 is a pointer where we set constant int pointer. And this means that we cannot change the value that we're pointing to through this pointer. We can still change the address that we're pointing to. So we can still say something like, I don't know, p1 equals, let's introduce a second variable here, int b equals 20. P1 is now pointing to the address of B. This works because this is not where the constant keyword is placed. Now, if we look at the other pointer, we can do P2 equals 20. And we can also see that this is going to give us a result when we print A. std endline. We're going to see that this works because here the constant keyword is after the pointer. So we say int pointer constant P2. This means that we cannot change the address that this pointer is pointing to, but we can change the value, or we can manipulate the resource that we're pointing to. So in this case, if we do it like that, if we say int pointer const P2, we cannot change what we're pointing to, but we can change the value of that which we're pointing to. So we can do that. We cannot do this with P1. So we can see if I do P1 equals 20, this does not work. This is going to give us an error because this is what happens when we put the const keyword first. However, we can still say this is now pointing to B, but we cannot do this with this one. So we cannot try to do the same thing for P2. We cannot say P2 is now pointing to B because P2 is a constant pointer of this sort where we cannot change what we're pointing to. And of course, if you want to do it hardcore, you can also say const int pointer const P3. I hope that's the correct notation here. So this, let's see if it compiles. There you go. So if we do it like that, we can do neither of those two things. So we can neither say P3 equals 20, and we can also not, let's first try this one. This is going to give us an error, and we're also not going to be able, where's the error here? We're also not going to be able to let P3 point to B, as you can see here. All right, so what are preprocessor directives? Preprocessor directives are statements that are executed by the preprocessor, which means that they happen before the compilation. These are not statements that are going to be executed during runtime or during compilation, but before the actual compilation. So what does that mean? If we have something like return 0, or if we have something like int a equals 10, those are statements that belong to the program, and they're going to be executed when we reach that certain point. They're going to be compiled to assembly, to bytecode, and then we're going to execute them when we get there. Preprocessor directives are not going to be part of the code in and of themselves. They are going to do something with the code. So there are statements that manipulate the code before we actually get into compiling the code. And we already have one of those preprocessor directives in here, and this is the include IOStream statement. Preprocessor statements are always initialized with a hashtag symbol, and we have stuff like include, we have stuff like define, we have stuff like undefined or pragma, or if defined, if not defined, and so on. And today we're going to get a little bit of an overview over those different statements. But first of all, let's cover what include actually does. What include actually does is, and this is why it's a preprocessor directive, it just copies the code that is written in IOStream and puts it in here. So everything that's written in IOStream, we just get it and put it into this file. This is what it does. It doesn't do anything fancy like linking stuff and so on. It just says, okay, take the code of IOStream and put it in here in place of this include statement. And because of that, we have all the functionality of the IOStream library. Now we're going to take a look, first of all, at the define statement, because that's a quite simple statement. And the define statement is just defining macros. So we can say, for example, I don't know, A macro could be just a constant. We can also say a macro is pi, define pi, and then in those parentheses we can say, okay, we want to define pi as 3.14159 and so on. This is just pi. And now what happens is that every time we see the keyword pi somewhere, we're going to replace it. So if I say std cout pi std endline, this is not the same as saying I have a variable pi or something, because if I would have a variable pi, what would happen is it would have to look where is this variable, it would have to load the value from there and so on. What we do here is we just replace the text pi with this number. This is done before the compilation. This is not something that the program does. We don't look for pi, we don't find its location, we don't load the floating point number. We just replace the string pi with the value 3.14159 and so on. This is all it does. This happens before the compilation, and if we run this, we're going to see that we get the number as a result here. So this is a macro. We can also do this with strings. For example, we can say define I don't know, for example, if we're using shared memory, we can say shm name, and we can say my shared mem or something like that. This is just a string, and whenever you write shm name, you will get that as a string. Now, why is this useful? Because it's best practice, or it's recommended to define macros for stuff that can change easily. For example, let's say you're defining or you're working with some sort of buffer or some sort of array that has to have a max size, and you have to work with that size on multiple different locations. And instead of doing something like int array, and I have 128 slots here, and then again I have to have a for loop that goes up until 128 slots and so on. Instead of doing that, I can define a macro in which I say array size or max size or something like that, and I can say 128, and every time I want to refer to that size, I just say something like, okay, initialize this integer array with array size slots. This is how you do it. And you can also say for int I equals 0, I less than array size, and so on. You can do it like that. This is what we use macros for. Now, we can not only define strings and numbers with macros, we can also define functions. We can say something like define square and pass a parameter a, for example, and then we would just say, okay, this means a times a. Now, this is dangerous though. I mean, let's first of all see that it works. Square 5, and you're going to see that the result is going to be 25. But it's dangerous because what we're doing here is we're just taking this string and we're replacing it with a times a. This is not the same as saying int square int a and then return a times a. And I'm going to show you why this is not the case. This is not the same thing, because it actually replaces this string here with this times this. And this is problematic because if I have a variable, let's say int I equals, I don't know, let's say 5. And now I want to say, okay, I want to square 5, but I want to square 5 plus plus, which means that I want to square 5, I want to get 25 as a result, but then increase I by 1. This is what we would expect to happen here. We pass I, we process I, and then we increase I by 1. So we would want to get 25, and then I should be 6. But of course, if we run this, we're not going to get I equals 6, we're going to get I equals 7. And this is because this statement here, I plus plus, is just copied. So instead of having I passed and I times I, we're getting I plus plus times I plus plus, and we're not even getting 25 because we're getting 6 times 5, and then we increase it to 7. So this is problematic, and you need to take care of that. So I would not recommend defining functions like that. So this is not recommended for functions. You can also try to work around with some parentheses and so on, but it's just not something that I would recommend. Don't do it like that unless you have a good reason to do it like that. So now let's take a look at another keyword, which is undefined. It's a very simple one, or actually undef. It just means that what we defined, we now undefine, and if I do it like that, we're not going to be able to print pi here. So you're going to see that we get an error. Pi was not declared in the scope, so the preprocessor is not able to replace it with anything. It's just not declared because we cannot find a macro, we cannot find a variable called like that, we cannot find a constant. Whereas if I don't do that, we're going to print pi. And also if I do it after that, we're going to be able to print pi, but we're not going to be able to print it after that undefined statement. And this can be useful if you're defining mathematical constants that have names like e, for example. So let's say we have e, and I'm not sure what e is, I think 2.7 or 1.7, I don't know, 2.7, let's say. And if we have a constant like e defined, the problem is that e is a name that is easy to, it's easy to find something else called e. And if you don't want every e in your code to be replaced by 2.7 or something like that, you would have to define it, use it, and then undefine it as soon as possible. So for the rest of the code, there is no constant, no macro with the name e. This is just a simple example of undefined. Now we can also have conditions based on those macros. So let's say I have some macro, I don't know, trigger or something like that. And then I say if this macro is defined, so if def trigger, then do something like trigger is defined, and end if like that. And if I run this now, trigger is defined. And if I undefine this, so if I say undef trigger, it's not going to get into that block. And of course, if I don't define it at all, it's also not to get into that block. But we're also not getting any errors here because we're just checking, is this macro defined or not? And if it's defined, get into this code here. Otherwise, don't get into it. And we can also do the other way around. We can also say if not defined, so if ndef, if not defined, then trigger, or then execute this code. And if I now go ahead and define trigger, we're not going to execute that code, as you can see. And this can also be used to check on which operating system you are. So if you're on Linux, for example, you can do something like if def Linux, and then you're going to execute a certain piece of code. So for example, you can say this is Linux code and so on. And you can do the same thing for Windows, if def Win64, you're operating on Win64 and so on. So you can do a bunch of different macros. I would just Google, depending on what you want to do, you can look for operating system macros, C++, or drivers, or anything that could be interesting. You can just check if it's defined, and if it's defined, you can do a certain execute certain pieces of code only if you're operating on a certain system, for example. Now, then there's also a keyword or a preprocessor directive that triggers errors. And this is very interesting because let's say I have condition 1 and I have condition 2, and both are defined. And let's say those conditions are contradicting. This could be something like, are you operating on Linux or on Windows? And if both of them are set, something has gone wrong. So we can say if def condition 1, and if also def condition 2, we're going to enter that block here. So do end if and end if. And what we can do to trigger an error so that we cannot compile is we can just say error like that. And if we're going to run this here, we get error because we get an error, obviously. I can also just write error like that to make sure I cannot compile. And then you're going to see that we are not allowed to compile because this just triggers an error, obviously. And last but not least, I want to talk about the last preprocessor directive that we're going to talk about today. It's called pragma once. And this is one of those directives that is not part of the C++ standard, but you can still use it because almost every compiler supports it. And this essentially means pragma once means that if you have, for example, two header files that include each other, and this is not something that you would do in the main CPP file, but let's say you have header file 1 includes header file 2, and header file 2 includes header file 1. what would happen then is, since you're always just replacing this with the code of the other one, you would get an endless recursion of I include you, you include me, I include you, and so on. And if you want to say this thing is only going to be included once, and after that it's not going to be included anymore, you can say pragma1. So that's the purpose of this preprocessor directive. So enum stands for enumeration, and it's a very simple thing. It's not too complex. The idea is that sometimes you want to have certain values that are simple categories. For example, let's say you want to have colors. For example, you have shapes and you want to assign colors to those shapes. So you want to say this circle is red, this circle is blue, this circle is green, but you don't want to use strings necessarily. So you don't want to say something like, I don't know, std string my color equals red. First of all, because you're not limited, you can provide any string you want and it's going to be a valid string. And second of all, a string is too overkill for what we're trying to do here. We just want to have a range of colors that we can choose, and then we just want to say this is red, this is blue, this is yellow, for example. But at the same time, using integers is a little bit confusing, because if I say int color equals 3, I can remember 3 equals blue, for example, and 5 equals purple, for example, and so on. But it's a little bit confusing for the programmers. So what we can do is we can use enums to do exactly that, have numerical values with labels. So we can say, for example, enum color, and inside of here we can say red, green, blue, purple, orange, and so on. And what happens then is we have this thing, this enum thing, that we can just say, okay, this is red, this is green, this is blue, and now I can do comparisons. So let's say I have blue here. And if I print blue, I'm not going to get the string blue. I'm going to get the numerical value that is assigned to blue. In this case, 2, because it's 0, 1, 0, 1, 2, 3, 4. So if I say orange, I'm going to get 4. Like that. And this is great because we can now also go ahead and say, I don't know, color, my color is red. And I can just print my color here. Looks like a type, like a class. And we get 0 because red is 0, obviously. And if I say blue, I'm going to get 2 again, and so on. And this is useful because later on, for example, if we have a class shape, for example, or a class circle, and you want to say this circle has a certain color, we don't have to say this color is a string or this color is an integer. We can say this color is the enum color. It's just a number. As you can see, this is just 0 to 4, but it's still with a label that we can use as programmers. Alright, so as the name already suggests, structs are used to represent data structures in C++. The basic idea is that you have a struct and you initialize it by saying struct and then a name, I don't know, my struct. And then you say this is my struct here, ended up with a semicolon. And the idea behind a struct is that you combine multiple things into one structure. So for example, instead of saying, okay, I have an integer and a string and a boolean and they somehow relate to each other, you say I have a struct. And this struct consists of an integer I, for example, an std string s, for example, and a boolean b, for example. This is just something here. Now this structure is one thing. It's one data structure. And in C++, it is a little bit like a class and an object. So for those of you who already know object-oriented programming from another language like Python or Java, for example, or C#, structs in C++ are almost like classes. Now, there are some differences. For example, the default, the members are public by default in a struct. It's not like that for a class. And also, it's just not considered best practice to use structs for things that you would actually want to use classes and objects for. So the basic rule of thumb that you want to follow here is if you want to represent a data structure, a classic traditional data structure, or something like that, you use a struct. And if you want to actually represent something like an object, like a human, like a book, and so on, you go for a class and an object, but this is not the topic of today's video. So structs in C++ are much more like classes, whereas in C, structs are really just data structures. You cannot go ahead in C and say, I have a void here, which is the method or the function test, and this function goes ahead and counts test like that. So this is not something that you could do in C, at least as far as I know. You can point to a function and so on, but you cannot just have this function belongs to that struct and so on. So what we can try here is we can just go ahead and say struct my struct. I'm not even sure if we need the struct, to be honest, but I think we need it, yes. M1, let's call it M1, and then we say M1.I equals 20 and M1.S equals hello, and then we have B, M1.B equals true, like that. And then we can just go ahead and say std cout M1I std end line, and then we copy that and we print the individual values. And last but not least, we can also go ahead and say m1.test. So we call the function from this struct. So when we now compile this and run this, what do we get here? No member named B. What is the problem here? Oh, it's a Boolean, obviously. This is not Java. So bool in C++, and then there you go. So we have 20, hello, 1, and test. 1 represents true. And now the interesting thing is that those are not, this is not the same as saying int I and string s and so on. Those values belong to this particular structure. So this structure M1 consists of an integer, a string, a boolean, and a function. And we can create another one. We can say struct my struct M2, and we can try to print those values for M2. Oh, sorry. In addition to that, can try to do that, and you're going to see that we're going to get different values, or undefined values, in fact, because we don't have anything assigned yet. So those are individual structures, and we can manipulate them. So the values of M1 are the values of M1, and the values of M2 are the values of M2. Now the function is the same in this case, so if I say M2 test, we're going to get the same result here. But if the function test, for example, prints information of the struct, so if I say, okay, print I, S, and B here, I'm going to get a different result for each struct. Now let's go ahead and do something useful. Let's not do my struct, let's do a person. So we can say struct person. Again, as I said, person is usually something that you would want to model in a class, so in object-oriented programming. But just for an example, we can use a struct for this as well. Especially because this is useful if you're doing something in C or even in Go. In Go, you also don't have classes, you only have structures. So you can get used to that as well here. We can create a new human or a new person. We can say struct person p1, and this person shall have a name. So std string name. Then we have not std int age. And let's say we have character gender, like that. And now what we do is we go ahead and say p1.name equals max, p1.age equals 25, and p1.gender equals m for male. And we can copy this and have a second person here. And this is going to be Anna. She is 35. And F for female. Of course, we need to change this to 2 here. There you go. And now we can also add a function here that just prints the info. So we can say something like void print info. And what we do here is we just say std cout name. I mean, yes, I could use formatting, but I'm going to do it like that right now. I hope I don't need something like this here, but I think not. But we'll find out in a second. H, and gender. Let's see if that works. We now just need to call this p1.printinfo, and then the same thing for p2. So as you can see, it works. It can access the individual attributes. So this works, as you can see, more like a class. In C, that's not possible. You cannot just do that in C, as far as I know. Maybe I'm wrong, but as far as I know, that you cannot do that in C. In C++, that's not a problem, and a struct can be treated like a class. Again, it's not best practice. But one more thing that we can do here is we can look at the size. So we can also go ahead and say stdcout size of p1, just to see how much or how many bytes this memory, this structure allocates in the memory. So we can run this here, and we're going to see 32 bytes. And I think for P2, it's going to be the same, obviously. I mean, hopefully, because I think maybe the name shouldn't make much of a difference here. Maybe if I add a lot of A's, but even then I think that the string has already allocated more than it needs. Yeah. But we can see that there is a change if we add something else here. So let's say, I don't know, we have a float weight or something. Even if we don't assign it, we still have a float. And because of that, we have 4 more bytes here. So type safety in C++ is actually a quite simple thing. It's not too complicated. The basic idea is you use the Typedef keyword. So you say Typedef, and then you specify a data type that already exists. So for example, something like unsigned integer, unsigned int. And now you want to use a different name for that data type. You want to create a new data type, but not, not a structure, not a class, nothing too complex, just another name. For example, you could have something like h. H is a type. You now want to have a separate type for h. You don't want to have just integer and then assign an h to it. You want to have h if it is an h. And the basic convention that you use here is always underline t. Now that's just a convention. You don't have to do it in order to get it working. You can also say my h type, and that's also a type. As you can see, it's highlighted like that. This means that it is a type in Visual Studio Code. And now instead of saying unsigned int value equals 10 or something, or h equals 10, we can just go ahead and say my h type h equals 10 or something like that, or let's do 20. Now this is now an unsigned integer, but it's of the type my h type. And this is important for type safety. It's going to be in the signatures. If you have a function that accepts a my h type, you can still pass an integer, but it's going to tell you, hey, this is actually my h type. So that you know what you're passing. So it has a lot to do with readability. If you have types for age, types for size, for example, one type that we already have in C++ is size t. This is actually a type definition. As you can see, it's just an unsigned integer as well, I think. So you could also just use unsigned int, but it's a type that you define for size t, and this is the type used for defining the sizes of arrays, for example. But I can show you that this is actually a number, so we can print it like that. We have a problem, unused. Oh, I'm not printing the h, I'm printing the type. Now it works. As you can see, we get 20 as a result here. And I can also do calculations with it because it's an unsigned integer. I can go ahead and add 60 to it, and it works the same way as with an integer. Now, as I said, this is not how you would do it. You would not just go ahead and tell and name it my h type. You would do something like h underline t. And the reason for that is just because it's a convention, because you know, okay, this is a custom type that I defined. It's not a class, it's not a structure, it's just a type definition. And you can see actually that Visual Studio Code recognizes that convention, because even if you write some nonsense here and then you follow it up with a underline t, it's going to highlight it as a type. So if I do hello t, it's going to be marked as a type. It's going to be highlighted. If I just do something like that, it's not noticed as a type, but if I do something like that, underline t, we get the syntax highlighting of a type, at least for a second. Of course, this does not work. You don't have a new type just because you do underline t, but that's the convention, and Visual Studio Code assumes that this is automatically a type. So this is how you define a basic type in C++. Now let's look at a concrete example here. We want to have a data type called byte, so byte like that. and it shall only allocate 1 byte of memory, and we want to do calculations with it. Now, of course, we already have data types that only allocate 1 byte or 8 bits, but those are characters and Boolean, and we also have another one. But essentially, those are not what we're looking for, because we don't want to deal with bytes in terms of calculations and call them characters, because you want to know, okay, is this now a character? Shall I treat it like a character? Or is this a byte, and do I want to do calculations with it, for example? And for this, we can say, for example, Typedef unsigned character byte. And now we have a byte type definition here. And I can go ahead and say byte b equals 70, for example. And I can go ahead and say cout b and line, like that. And the problem that you get here is that it's treated like a character because it is a character. And you can counteract it by just saying unsigned. And even if that's maybe not the most clean solution, maybe not the best solution, it works, and you can use it like that. So you can say byte b, and it's still better to know that you have to do this, because if you just call it character b equals 70, we don't know, okay, should I do this unsigned here, or should I actually treat it like a character? So using byte as a type is helpful here just because of the name byte, because the programmer knows, okay, this is actually a byte, and I probably want to treat it as a number here. Now, the interesting thing is that if I have a second byte here, let's say I have b2 equals 20, and now I don't use this unsigned here, but I just say b plus b2, I will get a numerical result because I can calculate the sum of those, and then it's treated as a number. Whereas if I have this directly stored into a third byte, so let's say byte b3 equals b plus b2, and then I go ahead and print b3, not b2, sorry, b3, we're going to get a character again, because it sees this thing as a character. It takes up 8 bits, therefore print it as a character. Now we can see that if we go ahead and say cout size of any b, actually b3 for example, we're going to see that we only allocate 1 byte, or actually 1 character unit, obviously, since this is by definition a character. But we also have a different way to do this. For example, we can use another type definition here. We can say something like Typedef int, or actually let me look what it's called, uint 8, underline t. 8 means 8-bit, so 1 byte. And I can call this my byte here. I'm not sure if that even works, because this in and of itself is a type definition. As you can see, this in and of itself is an unsigned character. So, you know, I could do that, but it's in fact the same thing that we did up here. This is one way to do it. And if you want a fancy way to actually have a type for a bit set, for an 8-bit bit set, you could go ahead and say Typedef. And for this, I think we need to include a bunch of libraries here. We need to include, and this is just fancy shit. You don't need to do that. This is just to show you that it works. We have bits and std c++h, and then include std int h, like that. And then we say std bit set, so we can define a bit set of size 8. And this is the byte type, for example. And now I can go ahead and just say byte type MB for my byte equals 100. And we can then go ahead and say cout MB and line, like that. And if it compiles, we get this in a binary representation. So if you actually want to use this as a real byte represented as a binary number, we can do it like that. We can also try to see what happens. I don't think that it's going to make any difference here. Maybe it's going to crash everything if I do unsigned. But yeah, it's not going to work. But that's how you can also define a bit set if you want as an extra type, byte type, or you could say 1 byte. bit set, but I think in fact that this is not even true, because if I do size of MB, we're probably going to see that it allocates 8 bytes in fact. So maybe this is not even a candidate for that. Yeah, no, it at least allocates 4 bytes, so this is not what we're looking for. Character is probably the best solution here. So if you want to define your own byte data type, you're going to use an unsigned character, and if you want to print it as a number, you're going to have to deal with unsigned as a function, so to say.